I'm the co-founder and principal solution architect at Clara, which is a professional services company around ZFS and FreeBSD. And so if you need support for ZFS or want to get a feature designed, then definitely come talk to me. So getting straight into things, ZFS has some scaling problems. Some of that has to do with the fact that it was designed quite a while ago at this point. We've been having this conference for 12 years now, and before that, ZFS has already been around for quite a while. And so when ZFS was designed, the future looked different than what it does today. We never correctly guess what the future is going to be. But hard drives got bigger faster than we thought, but IOPS didn't go up. But flash also took off maybe more than we expected. But even to put that all in context, the first SATA hard drive, as in transitioning away from IDE to SATA, didn't ship until the year after they started building ZFS. So, a lot has changed since when ZFS was being designed. And at the time, 1 terabyte was a lot of data, and a 10,000 RPM hard drive was fast. And flash was new. You were never going to have that much of it, and it was going to wear out if you used it too hard. And a lot of that has changed. But ZFS did a lot of work that very helpfully optimized for hard drives. Knowing that, hey, we have lots of CPU time, and the hard drive's always going to take somewhere in the measure of milliseconds to do anything. So we want to use the CPU and decide how we're going to lay it out and how we're going to request it, and can we aggregate this more to get the most out of the hard drive. And that has served us very well. But as we get to devices that are going to take single-digit microseconds to respond to things, we maybe don't have the same luxury to decide to aggregate a bunch of stuff and go to sleep and then wait for the result, when the result's probably going to come back faster than the smallest amount of time we can sleep for. And so some of the things that we thought would be true forever that really aren't. The first being that sectors on hard drives are always going to be 512 bytes. We learned the hard way that that wasn't true when 4K native came out, but as we're going to talk about later, it's going to get crazier than that. And some of the initial design decisions in ZFS might come back to bite us, and what can we do about that? And we also assumed that the CPU was always going to be faster than storage, that we would be able to take some time to massage the IOs before we send them to the disk, and that was never going to be anything but in the noise. But now the storage can often have lower latency than anything else, and we have to be able to deal with that. And we also assumed that avoiding seeking was actually going to provide some benefit. But now, everything that's not spinning rest, the seek is not even a thing. And so spending a lot of time trying to optimize for that, or even optimization of we assume the outer tracks on the hard drive are faster than the inner ones, so we should bias towards those. That's totally not the case with flash. Yeah, and because the latencies can be so low, sometimes we actually be better off not trying to do any massaging on the I/O before we send it to the device, and we just have to send it as fast as we can. So the big thing that I want to talk about today is what we're going to do about large sector devices. In your typical flash device, there's a flash translation layer that takes the concept of a logical block address that a hard drive had and maps it to where it is on the flash, so that as that flash wears out, we can move that data to somewhere else while it's still addressed by that same LBA. The problem is the flash translation layer has a granularity of the sector size. And so as devices have gotten bigger and bigger, we usually have up to 8 or 16 terabyte NVMe volumes now. The number of even 4K sectors on a 16 terabyte NVMe is a lot. And NVMe has to generally try to keep that table in memory in order to be fast. But that's requiring more and more RAM on each of these NVMe devices, and that makes them more and more expensive. As vendors look at building 150 terabyte NVMe volumes, or devices, they need to be able to save some money by not having as much DRAM on the device, and so they would like to go to a larger sector size so that their flash translation layer will be smaller and will fit in less RAM. So that means much bigger sector sizes. We've seen vendors talking about 32 or 64 kilobyte sector sizes. And in ZFS, we can support a 32 kilobyte sector size, but it comes with a lot of trade-offs that most people I don't think are going to want to make. And most of these devices will do a read, modify, write, and be compatible with a smaller sector size, but that's going to have a performance cost and a wear leveling cost that we probably don't want to have to make. So, what are we going to do with that? The biggest problem is obviously the Uber block ring. We have 128 kilobytes reserved for the Uber block, and if our sectors are 32K, then we're only going to fit 4 Uber blocks, which doesn't give you much of a window to rewind if something goes wrong. And so what can we do about it? So briefly walking over what the label at the start of a drive looks like today. We reserved the first 4 megabytes of a device. The first 8K is mostly padding. It's there because a lot of previous file systems assumed that first couple of sectors is where we might put the third stage bootloader or something, and they might try to clobber it, so we just left it blank to make sure nobody else would use it. That was originally 16K, but we carved off the second half of it to put the boot environment data. That was a collaboration between FreeBSD and Delphix to build a system where you can flag which data set to boot from next time and make it one time only, or to do the failed boot counter and a bunch of other stuff. So there's a little packed NV list in there that tells us extra instructions to use during boot. Then we have the VDEV config, which is basically the remaining 112 kilobytes there. And that, again, is an NV list. And it tells us about the configuration, a little bit about the pool, and about this specific top-level VDEV and its children. So if you have a couple of RAID Z2 VDEVs in your pool, on each disk, it will know about the RAID Z2 it's in and its kind of siblings, and that's it. And then the end of the first label is this 128K ring, where we put our Uber blocks that are generally 1 kilobyte apiece. But we round that up to whole sectors to avoid problems with shorn writes or just not being able to atomically update them. So that meant when we had 5 12-byte sector disks, if we take that 128K and divide it by the 1K of an Uber block, we had 128 Uber blocks, and that gave us quite a bit of ability to rewind or go back if something went wrong. But as we upgraded to 4 kilobyte sectors, it turns out we only get 32 Uber blocks now, which has mostly been enough, although we've definitely seen cases in the field where it would have been really handy if we had just a couple more. We ran into one case where some bad things happened and the Uber blocks got clobbered, and out of a couple hundred Uber blocks available across all the labels on all the VDEVs, there was one that was still the good one. And it made things quite challenging. It would have been nice to have a bigger ring there. And then we've started to steal slots out of that. The MMP feature for the multi-mount protection uses one of those Uber block slots for its sentinel of this pool still alive. So that means we only actually have 31 Uber blocks. And then if you store a checkpoint, that freezes an Uber block as well, and means you can really get even fewer Uber blocks. And then we have the second label, which is basically identical to the first. And then there's also a third and a fourth label at the end of the disk. And then the slack area is the rest of that first 4 megabytes, just to align the start of the raw data with this 4 megabytes. And that area is used on some operating systems for the bootloader, and is also used by RAID Z expansion as kind of some scratch space to bootstrap itself from, because it needs to temporarily rewrite the first couple of DVAs at the beginning of the VDEV. And so at the end, there's no slack area. It's just these 2 512 kilobyte labels. So after discussing it with Don and a few other people, what we're proposing to do is to take maybe the whole first gigabyte of a VDEV. Probably we'd only use this layout on disks that are at least a terabyte rather than every disk. We still want to support the case of small VDEVs for testing, and people are deploying VMs where they pay for every megabyte of space. They might not want to waste a bunch of it on Slack. But as we now hard drives generally are 20 terabytes and up now, and even NVMe are usually definitely over a terabyte at this point. That's kind of in the noise to just take this extra 1 gigabyte instead. So basically, each label would go from 256K to 256 megabytes. And partly to avoid compatibility problems and so on, we probably keep padding at the beginning for that whole first 16 megabytes. Part of what I assumed here is just a worst possible case that the sector size could go up as big as 16 megabytes. And so we want to make sure all the offsets in here are multiples of 16 megabytes. And so we keep the boot environment area. Maybe it doesn't need to be that big, but if that's going to be our smallest quantum, then everything has to be at least that big. And while we keep the name value pair thing we have now for each VDEV to know about its siblings, it might actually be useful, as long as we don't update it too frequently, to have the whole pool config on every disk. Especially when things get hairy, it'd be nice to have a known good copy of the pool config that didn't require reading from the MOS, which requires actually having assembled the whole pool again. This also means that when you go to import a pool where there's some missing devices, it can at least tell you which devices are missing, instead of saying, well, I know about these ones, and I know from the pool-wide config at the top that there should be n VDEVs, and I only see half that many, but it isn't able to tell you anything about what's missing. And so since we have all this room now, maybe we can take the luxury of storing the entire pool config in there. And then using the last half for the Uber block ring, having 128 megs instead of 128 kilobytes means that we can have as many as 32,000 Uber blocks with 4K, or at least 1,000 if we get all the way up to 128K sectors. And now we have a lot more ability to go back and look at what the pool looked like before and make sure that we can import stuff. And with a little bit of space left between those, maybe we have a completely separate area reserved for the special Uber blocks, like the multi-mount protection and the checkpoints for rewind and so on. But the other thing we might look at here is purposely setting aside in some kind of like round-robin database fashion really old Uber blocks. Obviously, if we have 32,000, we probably don't need any more than that. But if we're down to a smaller number, it might be handy to just be able to go back 5,000 transaction groups and say, what did the Uber block look like then? Whereas right now, when you only get 32, even just knowing 256 transactions ago would be really nice, but we don't have that. And maybe we'll find a use for it later. We don't want to have to perform this exercise multiple times. So if we're going to go all the way to gigabyte, we'll leave the whole last bit as scratch base. And maybe that'll also speed up RAID Z expansion, but we might want to define how much of that can be used for scratch base and how much is actually reserved for some future use we might actually have. And maybe we decide against some of these segments and keep more reserved space in each label in case we need it. But we'd like to have more conversations about that later today on what we can do around this. So some of the considerations for this, obviously, we want to minimize the time we're massively changing the on-disk format. So would like this to be a longer conversation and kind of figure out all the things we might need in the next 5 or 10 years and make sure we've reserved space for them. And for the things we don't know we need yet as we've kind of looked at the lessons of the last 20 years. But the other big question is, how are we going to identify the new format? Do we just put some marker in that little reserve space at the beginning that says, where older ZFS is going to look to find the old label? We have some dummy label that says, oh, this is a V5001 label or something. So the older ZFS will be like, I see that ZFS, but I'm not new enough to understand it, or something like that. Some easy way for it to define that. And obviously, make sure that if you try to import it, it doesn't say there's no pool here. It says, you need to upgrade your ZFS to be able to import that. But what are the trade-offs between bumping the version number again or just having that be a feature flag? The big thing is, if it's not going to be able to read the label, packing the whole feature flag list and so on into a dummy label is a lot more work than just incrementing the version number. But again, that's a conversation we can have. And then, as like I said, about maybe we decide where the cutoff is for switching to this new format. Obviously, if people have 100 gig disks, they might not want to give up a whole 1% of it for the labels. But at the same time, maybe they do for some reason, or because they know they're going to grow the disk in the future, especially in the cloud where the size of your disk is not as fixed as it is with real hardware. So yes, on to the next subject, which is queuing, which is everybody's favorite British sport. So there's a couple things that we need to look at with ZFS to kind of be ready for the future. The first one is when we actually issue I/O. With the way the VDEV queue works right now, the main time we decide to send more I/O down to the VDEV is A, when somebody queues even more I/O, or B, when some I/O completes. And the kind of context switching back and forth here can mean we end up spending a lot of time with nothing in the device queue because it completed faster than we would have really expected because it was designed for hard drives. So quote directly from the source code, every time an I/O is queued or an operation completes, the I/O scheduler looks for the next operation to issue. And maybe, part of that is just maybe we don't want to be issuing one operation at a time, especially if a device has 64 queues that have a depth of 64 each. Maybe one at a time isn't how we want to really consider issuing I/Os anymore. And also, maybe we want to lighten the amount of work done by the completion handler. When an I/O is done and we get a notification about it, now is maybe not the right time to be thinking about what other I/O should we send to the device, but instead just let's get this data back to the user as quickly as possible. The other problem is we do this one class at a time. So the VDEV queue is broken up into synchronous writes, asynchronous writes, synchronous reads, asynchronous reads, and scrubs. And we kind of issue from each of those classes one at a time. And knowing that we have 64 queues, maybe for NVMe devices, we should be issuing from all of the queues all of the time. It's not likely that the device is actually going to get saturated and not be able to handle the amount of I/O we're sending it. In most cases, we're not seeing NVMe devices getting to 100% busy very often at all. And so we might have to try harder or use more threads to be pushing I/O down to the device. And maybe what we should have is dedicated threads that are just for issuing I/O so that they're never context switching away. Another thing we might consider is it time for direct dispatch? Instead of after we issue the I/O, we go to sleep and some other thread gets woken up to tell us that it completed, especially the way NVMe works, each queue is tied to a CPU core. Maybe it makes sense that knowing it's only going to take 5 or 10 or 15 microseconds, that we issue the I/O and just wait for it to be done and then deal with it in line, instead of having as much queuing. But then we have to kind of auto-detect what's in NVMe and what isn't, and kind of have these different modes for the queue. And that gets complicated, but it may be what we have to do in order to push ZFS to being able to get the number of IOPS that these devices can. And then a conversation we had a bit yesterday about the kind of burstiness of I/O with especially asynchronous writes. Today, when you do a bunch of asynchronous writes, they accumulate in the dirty buffer in the ARC. And then when we go to flush that transaction group, we write out all that data in a big burst. We've all watched ZPL IOStat, and you see 0 megabytes written for 1 second, 2, 3, 4 seconds, and the 5th second comes and you just slam down 2 gigabytes of data. And then you go back to sleep. Nothing written for 4 seconds, and then on the 5th second, another 2 gigabytes being written. That works very well for hard drives where you don't want the head moving around a lot, and you'll get better read performance by not reading and writing at the same time. With NVMe, that's just not true. And then also, when we start looking at the cloud, often the device you're talking to is virtual and often has rate limits or I/O limits that are kind of artificial. Right? It's just this device does exactly this many IOPS, and you can never have more no matter what you do. If you're slamming down all the writes all at once every 5 seconds, you'll see your read latency is fine, and then there's a big spike. And it's fine and a big spike. When you're writing, you're using up all your IOPS, and then your read latency goes out to lunch. And so can we start writing some of that data sooner and kind of smooth out that 5-second burst? We can tune it so that we just flush every 1 second, but even then, that's still very bursty as opposed to just kind of writing data as it's ready. And then when we hit the transaction sync, we just finish out the indirect blocks and whatever's left.
How is it, as you know, with the drives getting bigger and bigger and bigger, and et cetera, how is ZFS handling the space reclamation issues, i.e. on SSDs, because that's to write a certain amount of blocks, they have to rewrite it again with zeros before you can rewrite it again. So is there anything ZFS is doing to kind of speed that up?
So right now, ZFS doesn't do anything special to deal with the fact that if you write too much too quickly, it can trigger the SSD to go into garbage collection in order to find space. That's usually a bit less of an issue because ZFS has, depending on how you configure it, been diligent about trimming the space so that the disk doesn't have to shuffle things around to find unallocated blocks. It already knows what blocks are unallocated. But it can still happen, and I know, Netflix has done a bunch of work in the I/O scheduler in FreeBSD's disk layer to moderate the rate of writes when it starts impacting the read latency. And it might be something that ZFS will need to look at as we start smoothing out our writes at some point. If, as we increase the level of writes, maybe as the write throttle kicks in when we have more and more dirty data, if we see it impacting the read latency, maybe we do want to try to back off and push back on the application saying, stop throwing so much data at me, you're causing latency on the reads. Not something I've considered yet because until we kind of smooth out our writes, we won't be able to see that happening as much. But it may be that the fact that we're doing this in big bursts is already making that worse because we throw the hard drive or the disk a big chunk of data and it has to go find space for it, and it might actually be making that garbage collection worse, whereas if we fed it smaller pieces, it would kind of do that in smaller chunks as it went.
Yeah, that sounds good. I was only thinking about that. You would be familiar with that.
Patrick?
I said Steve would be familiar with this. I was thinking about this largely in the video space because they do a lot of large writes and there's a lot of sensitivity towards latency and whatever. So that was kind of where that question came from.
Yep.
Cool, thank you.
And then the fourth thing, obviously, is queue lock contention. Because the way the VDAV queue works is we queue the work when it comes in and then we move it as we issue it, but we're basically keeping it on the queue. And so when we get a bunch of completions all at once, which traditionally didn't happen when you had a spinning hard drive with one queue, you got your completions one at a time. But with NVMe, you might get 64 completions at once, and all those completion handlers are now waiting to acquire the lock to take that one ZIO off the queue and mark it as done and call it done handler and so on. And so we can end up contending on the queue lock a lot just because our completions may become in bursts or are coming in faster than we can process them because of the amount of stuff we're doing in the completion handler. And so maybe can we use the kind of private pointer space that the bio layer of both operating systems provides to kind of attach the ZIO to the bio that goes down to the disk. So when we get the completion, we have a pointer to the ZIO that was completed and maybe not have to keep it on the VDAV queue so that we can still find it and call its done handler and so on, but without necessarily having to take a lock in order to do that. But if we do that, how do we keep track of how many are outstanding and especially find the one that we issued and somehow never got back? Although ZFS doesn't do anything about that now other than wait forever. So maybe it's less of a big deal. So the next item was, what do we do about huge disks? So whether that's the 150 terabyte NVMEs that we're going to build, a big array out of, or as I mentioned, things like Seagate's Core Vault, which is basically a giant chassis doing something like D-RAID in hardware. And so when you create a pool, you're getting a bunch of 700 or 750 terabyte LUNs to make a 10 petabyte pool out of. And the way we size things in ZFS is maybe not ready for that. A few terabytes isn't a lot anymore. So the first thing we have to consider is that every disk is not a disk at this point, right? Oftentimes what we're getting is either virtualized from a hypervisor or a cloud provider, or some LUN from a SAN or from something like a core vault that's actually an aggregation of a bunch of disks. And then sometimes it's a piece of flash or flash over the network or whatever else it could be. But between flash and virtualization and the various other abstractions, block storage doesn't necessarily resemble a spinning hard drive that much anymore. And what does that mean for some of our assumptions about it? And especially when it's something that's maybe virtualized or kind of hidden from us by other layers of hardware, how do we decide when to treat it like an NVMe versus when to treat it like a hard drive, if it's something that's kind of in between? And even if it's from a hypervisor, if the hypervisor has some cache, some of our reads and writes might have really low latency and make us think, oh, this is acting like an NVMe. But if we exhaust its cache, then suddenly it's going to be slow and act like a hard drive. So auto-tuning and auto-detecting might be a lot more difficult than we would hope. But there are other things we can do to lessen our reliance on assuming that the storage is going to act like a hard drive. With Delphix doing the S3 back storage thing, how much did that change how you treat a VDEV? The other question is about indirection scaling. If you have a 6 terabyte data set and it's all made up of 4K records, that gets really big. That means you have 1.5 billion blocks in that one file. And you have the full 5 of the 6 or 7 maximum layers of indirection in that file because you have so many billions of records. And how does the ARC hash table deal with that? We have a customer that has a 6 terabyte database that they cache in their 6 terabytes of RAM with 4K records. And the ARC does not handle that as well as we would hope. It gets a little better if you use 16K records and some compression, but we have a pull request open for multi-threading ARC eviction so that the read performance from the NVMEs isn't hampered by the fact that we just can't push enough blocks out of the ARC in order to accommodate the reads that we're trying to get, the speed of the reads we're getting back from the NVMe device. And so at some point, do we gotta consider larger indirect blocks, or at some point having adaptive indirect blocks? Maybe above a certain level, we should use a larger indirect block instead of just kind of 128K always, or even 32K always. Maybe it should hit, when we get to the point where a file is billions of records, maybe the indirects need to get bigger. We can't change the existing ones, but maybe we can at least make the higher level ones bigger so that we accommodate the total count more directly. And lastly, huge LUNs, as we've talked about on the leadership call a few times. If you get presented with a 700 terabyte LUN, our current logic for how to split it up into metaslabs is probably not the best. At some point, the metaslab logic changed to bias towards more like 3 terabyte size drives, which mostly made sense. But right now, you end up with usually about between 90 and 128,000 metaslabs of the smallest size that will accommodate the whole size of the VDEV. Probably need something a little better than that. How much memory a metaslab takes relative to how much memory a system has on average is shifted over the last 10 years. Maybe we can use a little bit more memory in order to have fewer metaslabs. We've seen some customers get pretty pathological performance when they have tens of thousands of metaslabs versus a smaller number, especially as Don found when using large records, the weighting we use for fragmentation needs some adjustment. And without that, we end up loading metaslabs that are not good candidates to find an allocation from. And when we're shuffling through tens of thousands of metaslabs, we often don't find the suitable space we want before we decide we've spent too long on this, just gang block it anyway. And that's inefficient on space, and also means that every allocation is taking a lot longer because we're shuffling through all these metaslabs, seeing that, oh, this one doesn't actually have 20 megabytes of contiguous space that I need to actually write a 16K record on a RAID Z3. One of the ideas we had there was just right now, we aim for 200 metaslabs, and keep increasing the size until we hit 16 gigabytes per metaslab. And then we increase the number of metaslabs until we hit the maximum. And then we just increase the size until we come down to below the maximum. Maybe it makes more sense to alternate between doubling the size and doubling the count until we get some kind of middle ground for what's the right count of metaslabs for this device. But yeah, the weighting, it seems that when we came up with the fragmentation weighting, we didn't, 16 megabyte blocks weren't really a thing yet. I think we only supported, 1 megabyte unless you set a tunable to let you go higher than that. And so a lot of the selection logic assumes, search ahead for the next 16 megabytes of space. But with RAID Z3, to allocate 16 megabyte record, you actually need 20 megabytes of space by the time you include the parity. And so we consider any metaslab that has 16 megabytes of contiguous space to be not fragmented at all, which means it looks like it'll satisfy this 20 megabyte allocation, you load it, and then it won't. And so, we need to look at that. And I think in general, across a bunch of different places where we use that 16 megabyte limit, we didn't consider that a 16 megabyte record isn't always only 16 megabytes. It might actually be more. And so there's a bunch of places through the code that we're going to need to look at and decide how to improve that. And what is the right number? Or, is there a new define we need that is, this is the amount of space we need to do just one allocation, if it's the biggest it can be with the worst properties of being, a RAID Z3 gang block or something. So to start wrapping that up a little bit, our key takeaways are we need better support for NVMe, especially knowing that they're only going to get faster. Like even today, for Micron, you can get a 3.84 terabyte NVMe that will do 1.6 million 4K random IOPS and will easily do 7 gigabytes a second. And you build a pool out of that, and you only get about a third of that performance on the IOPS. If you go to bigger sector sizes, you can even bigger record sizes. If you use 16K records, you can get pretty close to saturating that, the full 7 gigabytes per second. And the default 128K will have no problem getting all the bandwidth out of that device. But when you go down to 4K, you're only getting about a third the IOPS. And importantly, as you add 2 or 4 or 8 of these NVMe, the performance doesn't go up at 4K. You can't get more IOPS no matter what you do. It looks really strange to stripe 4 NVMEs and get the same performance as you get from 1. What can we do to solve some of those problems? Obviously, the large sector support. We've already seen in the field a customer with a low endurance NVMe that has a 128K sector size. And they kind of naively installed ZFS on it and set up their ZVols for their virtualization. ZFS at least auto-tuned to a maximum A shift of 32K. But that meant their ZVol with a vol block size of 16K, as they wrote the VM to it, they're like, we've only written half the size of our NVMe, but our NVMe reports it's out of space. Where did all our space go? Because every 16K on the ZVol took a 32K allocation because that was the A shift size. And so once they half-filled the pool, all the space was gone, and they were very confused. And so on top of the fact that we don't support that large of a sector size, and we have all these problems with the Uber block ring not being big enough when we're going to have a 128K sector NVMe, we also have the problem of, do we need to teach the ZVol to have a different default of never less than your A shift size? And how do we warn the user about the sector size? And maybe we decide that on some of those 128K devices that support emulating smaller reads and writes, that we don't shift the A shift all the way up to 128K, but what's the right trade-off there? And then, like I said, capacity scaling, the individual LUNs or physical devices that we're going to build pools out of are just going to keep getting bigger. Beyond tuning the metaslabs, what else can we do to make sure that we're going to support that properly and not run into scaling issues as we get, to triple digits of petabytes in a pool. And lastly, how do we continue the long-term maintenance of ZFS in general? As we keep adding more and more things, and as the industry shifts a bit, we're picking up a lot more users, and so the kind of ratio of users to developers is more biased towards the users now than it was in the past. And how do we make sure that we can keep up with the incoming rate of bug reports and issue reports and pull requests and so on, and make sure that we continue to scale our ability to respond to the community and to grow the developer community by turning some of those users into developers, and make sure that ZFS continues to perform well and be the best solution that it is today. And how do we keep our testing infrastructure up with the rate of change? And that'll segue into Don's talk after mine, as we kind of talk about what we can do to keep growing the testing framework and making sure that we're finding as many of these problems before we release them, rather than only once users report them. Okay. Are there any more questions? Patrick, which number?
Recently, we had some look on ZFS detection, import process, or earlier process of actually detection. Do we have actually pools there? Mm-hmm. We had a look on Linux block ID code, and appeared it's completely not matching with what ZFS does. It needs complete rewrite. But as part of rewrite, we hit again question that current design of the label is not exactly oriented for quick checking whether we have something on pull on disk. Mm-hmm. So the first things, obviously, like on a wish list, I'd like to have is some sort of easy signature. Just in a label, read one sector, see signature. Okay, this is definitely ZFS. You don't look for sectors, found 0 signatures, definitely not ZFS.
Yeah.
So as part of designing new format, that's one thing I'd like to have. Second part.
I really think that just putting, every Uber block has its little
that's
signature,
Uber block,
but something in the label that's just read the sector, and if it just says ZFS, ZFS, ZFS over and over again, we know, okay, that's a label, that's a pool, we should look closer.
The problem we actually hit is that some disks imported from early ZFS version, such as L2ARCs and Spare, they don't have any Uber blocks.
Yeah.
They don't need Uber blocks. They don't update them. So, and block ID code actually looking for a signature of Uber blocks actually failing because there is no signatures. So we need signature as part of a label.
As just part of the label, so that at these 4 offsets, you will see this thing, and that means it's ZFS, even if it's, like you said, just an auxiliary VDEV.
Second part, second issue we hit is that actually to read and release, you need to read all that 120, 118 or whatever, 112 kilobyte of space, and then try to look, is it in released? Does it look like in released? And so on. And you don't have any sort of knowledge how big shall it be. Mm-hmm. And in context of you jumping to next, like 1 gigabyte.
Huge, 128 megabytes. Then,
like I definitely don't want to read gigabyte of space to find out do we have any labels there. So I think your design should be slightly different. I think that we should have small, some anchor block or header or whatever you call it. You should have include signature and maybe first small NV list with pointers to other extensions, whatever may grow later. I'm not sure we even need that separation on multiple separate areas, sub-areas for different reasons.
Right, if we make an NV list that just says this is here, that is there, then we have a lot more flexibility in the future.
Yeah, so just gives this general area and offsets within that NV list to the other chunks. We need to compact, we may start compacting them together to easily read in one operation, pretty small, scalable from small hardware, and also can be easily grown to later hardware.
Yeah, I really like that idea.
We could potentially not even separate all those 4 headers by 256 meg. We could put them in old locations originally, where within some padding or whatever areas, and then play compatibly potentially. We can point either old locations to the question of compatibility, or if we need more space, then sure, move them out, and that pool will only be importable by the new ZFS, obviously.
Yeah.
Something that knows about that header block. So that was my second comment, that we need some sort of header to avoid reading
more than we need to, and it gives us a lot more flexibility to change how we're using that label in the future. I really like that.
Is that something we can do ahead of time?
Well, basically, as part of the redesign, we would,
What I mean, like right now, I'm deploying X amount of petabytes. I don't want to have to go and redo that in 6, 8, 12 months.
right. So
Can I resize that initial one during deployment now in prep for that?
currently, there's no way to repeat the question from Stu. Is there something we can do for pools that he's deploying right now to be prepared for this? We don't plan for this to be something that would happen as part of the upgrade. So, if you build a pool, its label will be the current label. We might be able to get some of what Matt's talking about of, we stick the header NV list maybe as part of the boot environment area. Or no, we overwrite that though. Anyway, we'll find a good place to put this NV list that will make the label more extensible. And it will mean that in the space we have for an old-fashioned label, we would be able to have more flexibility on how we use that space, even if that is just, our VDEV config isn't using all 112 of these kilobytes, we can use some more of that for the Uberblock ring or something like that in order to give some of these advantages to pools that were created with the old layout instead of the new one. But currently we don't have anything where we could say, align the first DVA with the 1 gigabyte boundary instead of the 4 megabyte boundary in order to leave us room to grow the labels in the future. Paul?
Yeah, so, I mean, obviously I think there's a lot of really interesting stuff here to talk about, and happy to talk about a bunch of it offline later, but specifically for the sector size stuff. The thing that I was thinking, and I think this ties into the point you were making, is that the choice of 16 megabytes as sort of like the worst case scenario, do we have like specific data that suggests that is an actual sector size that will be targeted, or that it is the biggest sector size that will be targeted, or does it make more sense to do something more dynamic, where we can say like, oh yeah, the sector size for this device, when we create the pool, we're like, okay, the biggest sector size we're going to have for this pool is 32 kilobytes, and so we size all of those things based on that size rather than pegging it to some biggest size that we're ever going to encounter in the future.
Right, so the biggest size I picked there was just from the max record size. If the sector size is bigger than that and we can't have a record as big as the sector, then we're always going to be wasting space.
Right.
But yeah, kind of to Mav's idea, we could, by using a header, we can make it a lot more dynamic and not have to give as much. I think we might still benefit from reserving that first whole gigabyte, but sizing everything based on a more realistic max A shift for the time probably does have a lot of advantages.
No, aside of Uberblock, everything else will likely write in one go, in one operation. So we could just pack them together to write them together to not bother with this here, this there, this there.
Yeah, it might even, like you said, probably better performance to write them all packed than to, write 32 kilobytes here and then seek and then write another 4 kilobytes there and seek and write another 4 kilobytes here and so on.
And one more issue, not directly related, but we hit with block ID with pool detection, that if you create a ZFS on top of ext4, on top of VMFS, on top of Linux RAID and some other cases, block ID detects those first, even so ZFS was the last, with such a big amount of holes that we never overwrite. We may not be able to import the pool we legally created just before that.
Yeah, so we might also take to kind of prophylactically zeroing out the label before during zpool create, so that we get rid of whatever ext4 signature might be in that first 8 kilobytes of padding that we don't normally write it to the label, and make sure that block ID isn't going to pick up a bunch of stuff that is from an old, like we've seen this problem on FreeBSD, where if somebody had used the motherboard RAID and that signature was there, the GRAID driver would see it, and then it wouldn't be, ZFS would say that disk's in use, I can't use that one, and we don't I looked at something with like gpart of like, wiping the first and last 1 megabyte of the drive or something, but maybe zpool, when we're creating it, we should, try a little harder to make sure there's no other cruft left on the device.
No, yeah, it's maybe a bit of a hack, but instead of like, if we leave first 32 megs of disk campaign, we can collect all the problems we could. It would be worst case.
Yeah.
While writing from the beginning, it would give us slightly higher chance of actually.
Of clobbering all the leftover gunk.
Yeah.
Paul, go ahead.
The thing I was thinking about when you were talking about the meta slabs for the like ultra large VDEVs, I did a bunch of work on meta slab performance not that long ago, so that definitely I was thinking about a bunch of things there. But one idea that occurred to me that's relatively straightforward that wouldn't require a lot of other changes is that like there's no particular reason that one VDEV has to contain exactly one meta slab group. You could have sort of like internally sharded that VDEV into 10 meta slab groups that would, have a smaller total size, and then you could like, they would be able to be treated by the rotor just like having multiple separate VDEVs would. Mm-hmm. And that would also mean that like metadata would get stored at different offsets in these giant disks, which might help improve reliability in case like they have an underlying storage failure or something like that. And also would bring the meta slab sizes down so that you wouldn't have
Massive.
And the counts down, so you wouldn't have quite as catastrophically bad of a time when searching for space.
Yeah, I think that could be very useful. And Don has been toying with the prototype idea of being able to grow the size of the metaslab to reduce the count on existing pools by just, take these 4 small metaslabs and combine them into one and kind of work through the list and rewrite them all.
Nice.
But yeah, I think possibly having multiple groups could also be a good way to scale on these supermassive disks.
Yeah.
Of many meta slabs that we have to
Patrick, can we
update
get-
all of them.
Oh, okay.
So a problem with all the many meta slabs that we may have to update a lot of them.
Mm-hmm.
We have already a shared log, but we need to flush it sometime. I'm not sure that reducing number of meta slabs save us dramatically, or reducing number may help. But I'm not sure how sharding would help unless we start preferring fill those completely until we even start thinking about others.
Mm-hmm.
Right now we prefer the best meta slab we could, but maybe we could remember what we were doing last and continue. No, while we are running, we should do that. We continue running the same meta slab until it got a threshold worse than the next before switching. But maybe we could extend it for longer periods of time.
Yeah, and I think, Don, you also found that once we hit half full, we move on kind of too soon sometimes?
Well, when you're allocating big blocks, yeah, it just gives up and goes somewhere else. And then your entire pool is all ends up at half full.
Yeah, and so there's probably some more behavior changes in there. Go ahead, George.
Yeah, and I think the other point here too is that as you start doing big blocks, you may want to segment big blocks to certain meta slabs while your metadata, which still remains relatively small, is being written to different meta slabs so that you don't end up creating more fragmentation as you, like if your allocations are mostly like 16 meg and then you're throwing a 4K block in the middle, when that gets freed up, that space is really only going to be usable by other metadata. So you're going to have to figure out like how you kind of balance that, and maybe with these large drives, it's obviously a little bit easier.
I think we could take a look on allocator code, because right now allocator is by default, it tries to split allocations by power of 2. I'm not sure how much reasonable is that, since we have compression for a long time and now sizes are pretty random. I was thinking we could maybe just within MetaSlab, instead of having 32 or 64 pointers, we could have, okay, if this is part for smaller blocks, write sequentially, that part try to dedicate for bigger one and write sequentially. As we can write sequentially, okay, we'll wrap around to do something else, but I don't think logic of power of 2 actually makes sense. So maybe we could, like with embedded slog, differentiate by usage. I'm not sure was it separation of data versus metadata makes sense or something else, but if we could predict keep time of the data, how long they will be on a disk, maybe that we could group on.
Yeah, I wonder if there's advantage of if most of our metadata is packed into one metaslab, if that means we can aggregate the reads better sometimes. You know, when we're reading a super large file that's going to have a whole lot of tiny bits of metadata, if they happen to have been all allocated from one metaslab, maybe they're a lot closer together when we need to read them. But then again, over time, maybe they're not.
No, we would need to write files completely sequentially, or for most part sequentially, for the indirects appear into nearby blocks to actually matters. But I wonder, would it allow us to reduce overhead, maybe, write inflation? Because right now we are writing metadata, then we're updating space maps, writing, and it's then we deleting something, and again updating the space maps, and it's not even updating in the same metaslab. We write in one metaslab while dirting several others. To flush those, we update a few more, and it's total noise through all the pool. Yeah. If we could maybe localize that. Right now, metaslabs are space maps not stored in metaslabs themselves, they stored anywhere, and that creates weird effects I saw.
Yeah. Paul?
Yeah, I mean, so this is a slightly separate topic of discussion, so if other people have points on this, we can go to them first. But another thing that I was thinking about when you were talking about, like, how do we know what kind of drives the user is using, like how do we like get that information so that we can like properly plan our queues and our like access patterns and all that kind of stuff. It feels like as storage there's so many more storage options now. It feels like one thing that we might want to do is have a, like in addition to the existing zpool create and zpool add interface where you like specify sort of your VDEV patterns in these like, in this very short format, it might be nice to have like interactive zpool add where you can like build the tree and like it'll show you what the disk layout looks like. This would also help with people who like accidentally do attach instead of add and things like that. Mm-hmm. And then we could also have a way to say like performance hits where the user could say like this disk is an NVMe, and so like we would know when we're doing our planning what things look like there, and like we could give the user the option to provide more data and hopefully use that to make better decisions.
Yeah, like we've also considered that for VDEV properties. Like how do you specify VDEV properties at zpool create without making the zpool create command line atrocious? And so maybe interactive lets you do that and would let us ask people, you know, hey, while you're here, do you want to configure how many checksum errors per 15 minutes will trigger replacing this with a spare? Or, you know, if a disk is slow, do you want to auto replace it or not? And that kind of configuration in addition to, hey, can you tell us something about what kind of disk this is? Because that would let us suggest the right tuning for you, and kind of to Mav's point of yesterday, lead to users not twiddling the kernel module parameters themselves as often as possible.
Which is still fun for some of us. But
Stu, can we get Stu's
But
mic?
what we talked about on Saturday was actually having a profile of, hey, here is a standard set for spinning disk, standard set for NVMEs, a standard set for, we actually tried 1 petabyte large LUNs, sucked. 500 was, you know, through marginally excessive testing was the high water mark for that. So figuring that out ahead of time as part of the testing plans and everything else, hey, here's the feedback from us dumb users to say, hey, here's how we need to tune to actually get the performance we're expecting out of really expensive hardware.
George?
With like the NVMe work that you were looking into, is it possible to discover like how many queues are the drives actually reporting that information back, and do we have kernel interfaces to actually get that?
Yeah, so they report it to the OS. Whether ZFS can easily get that or not is probably very platform dependent. But to some degree, yes, that you can actually find out from the device that, hey, I have 63 queues with the 64th one reserved for admin commands that have, you know, a queue depth of 64 or whatever.
If it's not abstracted away by
Yeah.
virtualization.
Yeah, and then
That's where the tuning side of it comes back into it, of, hey, I know what's really happening at AWS, this is what I need, versus real hardware.
out and probes the drive a bit and says, here's what performance I can get out of it doing.
But
a set of
what it's
operations.
giving you, from that probe test, an AWS or GCP or whatever is saying, no, you're getting this drive and it looks like
Yeah.
you're not getting the real stats underneath of it. However, it is a tunable, in my mind, to be able to go and fix that versus, hey, here's physical hardware, here's a abstraction layer. And
Yeah, and we talked a bit about that earlier in the presentation about like, yeah, we could do some tiny benchmarks and try to make a good guess from that, but how do we make sure that the hypervisor doesn't happen to have cached the first couple of reads and so we get this performance, but then later we get that, or even consumer grade NVMe devices have a limited amount of SLC, and so they'll write really fast up until they fall off a cliff and then they'll write really slow. And how do we try to discover that other than, oh, we're just gonna throw a terabyte at this disk and see if it ever slows down and things like that. But yeah, we can at least do something, even if it's not perfect, because it'll get us better than just assume everything's a hard drive and it's up to the user.
80% of the way there and the rest is tunable. Fantastic.
Right, yeah, so you want probe plus hints.
Right, yeah.
Can we get Steve's mic?
Could you talk a little bit about what you see as sort of the low-hanging fruit in terms of concurrency, adding more concurrency? You talked about the separate queues of async writes and the scrubs and everything is sort of serial today. What do you sort of think as low-hanging fruit versus like hard stuff to do in adding concurrency?
Yeah, I think possibly the low-hanging fruit is looking at, can we get dedicated threads just firing I/O at the disk, but at the same time, with the fact that each queue on an NVMe is per CPU, maybe that's not the best way to do it. And we actually want to do more like direct dispatch. So when an application is running on CPU N and does a write, we want to put it into that queue for the NVMe, and rather than going to sleep and letting some other thread tell us when we should wake up and continue processing that, we directly like sleep on it and get the answer back really quickly and return to the user while all the other CPUs are doing the same thing on other queues. But if you're doing that, if you're doing direct dispatch, how do we make sure we're actually getting some queue depth as well? If you only have 32 CPUs and you're using 32 NVMe queues, then if you're only going to have one command in each, you're probably not going to get all the performance either. So what the right trade-off is not completely clear yet, but we've seen that there's probably a decent amount of low-hanging fruit in that area.
All right, well, thanks a lot, Alan. So we have about a half-hour break, and we'll be back at 11:10 for a dawn stop.
All right. And I'm happy to keep answering questions over here.
corrupted the pool, but it did what you tested it to do, and it just keeps moving on. On the flip side, Z-test is very narrow in scope. It's testing the DMU layer of ZFS, the pool configuration layer, some of the ZAPs, the ZIL, the ARC, sort of the main core of ZFS. And the scope, of course, is to stress it out. We're going to try to break it, essentially. And the runtime is, by default, 5 minutes. You typically run it short burst. You can run it longer. The longer you run it, the greater the odds you're going to eventually find one of the unfixed bugs that are still in ZFS. And then finally, as far as integrity checking, it'll actually intentionally try to corrupt the pool. And then at the end of the session, or after it crashes, it will run ZDB. So it'll validate, all the checksums. It'll validate like the space map law, all the integrity of all the different components in ZFS. Check for leaks, whatnot. So it's good. It's good in that it'll break your code potentially, and then validate or validate that you didn't corrupt the pool. Again, the scope in this picture over here, there's like ZFS has an interface layer. It could be whether you're doing admin commands or POSIX commands. That whole way that you think of getting into the insides of ZFS. We're not testing any of that. We're going to test basically the core functionality of ZFS. We don't cover, obviously we don't cover the SPL, the Z layer. We don't do ZVols, Z events. Don't test send and receive, channel programs, and then the BDEV disk layer. We're not interfacing with the block layer or engaging any of the kernel in terms of the I/O that we're sending out. So why is it stressful? Well, we're going to do a lot of stuff in parallel. We're going to be creating and destroying data sets on the fly, while we're reading and writing to other data sets in the pool. We'll be constantly changing, the compression, what compression we're using, what checksum we're using, whether or not we have encryption. We'll hey, let's turn encryption on. Let's turn it off. Let's make use this checksum, and it's like, no, we'll switch it over to this one. All the while we're changing the pool configuration. Where, hey, let's add a slog. Hey, let's remove a VDEV. Hey, let's do RAID Z expansion right now. It's like so. A lot of churn in these different layers. And all the while, it's changing data set properties. Hey, my record size is 4K. No, in the next second, it's 128K. So it'll pick, when you run it, by default, it'll pick a configuration. It'll like a mirror, a RAID Z, or DRAID, and the appropriate number of disk to run that config. And it'll spawn, in addition to the kernel context, which is going to have all your task queue threads, your transaction sync threads, all the threads that the kernel normally has. It's going to instantiate all those. On top of that, it's going to spawn 23 threads to go bang on ZFS. And then there's up to 7 data sets. Typically, by default, you can put more in there. And there are currently, at last count, there was 38 individual tests that we're running. It'll pick a random test, run it, and then come back and do another test. And up to 5 top levels. So if it picks DRAID, it's going to test DRAID with one top level DRAID, and it's going to make another one. And it's like really stress it out, because I don't know in real life if anybody's actually deployed 2 top level DRAIDs. But Z-test will certainly do that. And as I mentioned earlier, it'll inject random garbage on some of the leafy devs to confirm that the self-healing works and confirm that like RAID Z construction works when one of the disk is damaged. I mentioned we run it in a process. So there's a main process when you run Z-test. It'll spawn a new process, and that child process is like simulating the kernel. And the advantage there is like we can kill that process right in the middle, whatever it was doing. And so 70% of the time, it'll kill the process. What it does is it starts out with like a 5-minute goal, and every 60 seconds, it'll either like unmount the pool, remount it, and go do a new set of tests, or it'll, in that one segment, it'll just kill it. And so you'll see that in the summary. It's, I like to think of it as everything, everywhere, all at once. Oops. This is where I think the internet went down. See, I go up, go down. Is the internet up? What's that? Oh, you mean go yeah, okay. No.
But in the sidebar, I can see the next slide.
Yep.
All the funny colors. You just click it, it's loaded.
Okay. Well, I want the slideshow to start there, so let me see.
Go to the broken one, and then the background look all for it.
Well, let's see if we can bring up this. There we go. Okay. From current slide, I'm clicking you. Yeah, it's having trouble rendering it because it's.
Everything on that slide.
You wanted everything everywhere.
Yeah, this demonstrates the topic. Yeah.
During the 70% build period.
Wow, I've never seen it do that before. Okay, worst case, I can go back to PDFs, but okay. Anyway, the slide I wanted to show in the slideshow was everything, everywhere, all at once, and sort of summarizing what I was talking about.
Another access point if you want.
Okay, I think we're fine. So yeah, so it's banging on the disk. It's like has a number of data sets that it's just doing random things on, and all the time. So let's see if I can go back from here. Okay, well, let's do this. Sorry about that. I didn't have control. Send a slideshow. Okay, sorry about that. Note to self, don't use live internet for your slideshow, which was fortunate because I was hoping to do a live a demo later. But so as I was mentioning earlier, there's 38 tests. You can see here, I won't read them all, but there's like stuff that's gonna to hit the DMU. There's stuff that's gonna be doing SPA config, all those type of things. And then VDEVs, like we're gonna be doing all kinds of things that you wouldn't normally be doing on a live, like adding VDEVs while you're still writing to it. Typically, you're quiesce your system and you add a VDEV or something like that. This is all going to be happening dynamically. We do a little bit of the ZIL and the ZAP, mostly just sort of in combination of other tests, but there's a little bit of coverage there. And then we're specifically testing some specific features like MMP or RAID-Z expansion or things like that. And this slide, I apologize, I don't know if anybody can see it other than me. Well, that part where it says calls into the SPA layer directly, I'll just read it. It's doing a SPA config enter, which, if you're familiar with the SPA layer, that's the big global lock before you do anything. And then we're going to go find the top level VDEV. And then this is device removal. So I guess it passes in something. So, and then we're going to exit the lock. So we have our VDEV. It's been safely gotten. And then we're going to just call into SPA VDEV remove. And then we do some error checking. But so that most of the tests are similar to this. You get past a little bit of context. The ID is the thread ID. So you can, if you have, say, like your 7 data sets, you can, you know, modulus that ID to pick a data set, basically. And then run your test. And most of them are like this, very short, very specific. But bear in mind, there's 20 other 3 threads. They're also running a test. So sometimes, like in this test, yeah, you can't see it. We take a VDEV lock, because we know we're doing something with VDEVs. And so we sort of protect ourselves from doing too much damage. Yep.
I'll be sure the answer is yes, but since I admit I haven't really used this live or anything, but if you have a environment where, you know, typical customers, users saying that things are behaving slow, whether it's read or write, is there a way, can you use ztest to kind of test that real time, to kind of try to duplicate whatever they're saying? If they're saying, hey, we're having a bunch of read issues, and you can say, well, let me just run ztest for like 10 minutes and then see.
No, not really, because the randomness of it, it's not doing a
Okay.
specific workload. It's just doing sort of, there's some tests that will do a bunch of writes and stuff like that. But it's good for testing out a config, and I'll get to that in a second. So like if you always do a certain draid, raidz config, you can run ztest that way all the time. So whenever you make a change, what I do a lot of stuff with raidz, so every time I'm done touching my code, I'll go run ztest with the raidz config to make sure I didn't break anything. Of those tests, we'll run them with a frequency that's, whoever wrote the test, they can say, hey, I think this is very important. I want you to run this all the time. Or I recently added a test for pruning the DDT table, which is like, we don't need to test that often. So I put the rarely option. So, you know, every 60 seconds, it might randomly choose that one. So for example, yeah, like the DME read-write test, we run that all the time. That's just like running almost every, if you just did a profile, you would probably be running that test. On the other side, reGUID, we just, that's not gonna break anything. It's a very simple test, so we just run that fairly infrequently. As I mentioned earlier, we do test integrity, and we intentionally write garbage on the disk. We do other things that, you know, we'd want to make sure that the integrity is correct. So that's covered by either on import, we'll run ZDB, or we'll potentially kill the process. It should be safe. CFS is copy on write, and we'll verify that by running ZDB. So why would you want to use ztest? My thinking is, why wouldn't you be using ztest? But so first, you know, as I alluded to earlier, it's like it'll find the bug you introduced. If you break CFS fundamentally, almost like when you run check style before you do your pull request, I think it's warranted to run ztest. It only takes 5 minutes. And it gives you confidence that you didn't, you know, embarrassingly break CFS in a fundamental way. It's also good to exercise if you're changing code, the new code paths that you're working on. You want to get some exercise. You can run ztest. I often use it to test out some theories if I'm curious, like how a certain part of the ZFS code is working. I can I can put some printfs in there, or and then just fire it up, and I can see as Z-test is running, like what it's doing. It helps me understand how the code is working. Obviously, it'll help catch regressions. And then another benefit is that I'm not going to set up multi-host protection. I mean, that's just, I got to set up 2 servers, all this. Or same thing with D-RAID. It's like, oh, I don't have 20 disks laying around. But Z-test will test that for you. And like gang blocking, some of these things where they don't normally come into play, it'll test that to make sure that it's working. Basically, to run it, you just type Z-test. I'm intending to fix it. It used to be non-verbose if you didn't specify verbosity. Right now, you see a bunch of spurious stuff coming from the kernel that I'd like to clean up. But as far as Z-test output, -v will give you some terse output, and more Bs will give you like more and more information about what it's doing, what it's running. As I mentioned, you can test a specific config. So like in this example, I want to test RAID Z. I'll specify how many disks I want, how much parity I need, and the size of the disk. It will, right now it'll create 7 512 meg disk, but I didn't specify the top level, so it would make up to 5 of those. So 35 disks could be made in the run of this test. And then this is just sort of a hand-picked. I don't know if you can see that either. It's coming out fluorescent over there. But at the end of the run, it'll tell you what pass it was, whether or not it sig killed it, whether or not how much space it's using, how much time is left on the clock. And so this is giving me a summary. And look, there's a bug. It says in my 30 seconds that I ran, it said it ran 8 minutes and 26 seconds in DMU write parallel. That's not possible, so we'll have to go fix that. So Z-loop. You can run Z-test. You can run it. You can specify a time for Z-test, and it'll run, but it will only be running against whatever default config it picked. So if you want to run it for a long period of time, it's probably more advantageous to have it check multiple configs. So that's what Z-loop turns Z-test into like a longer running test. And then the other thing is if Z-test crashes, you ran it overnight, but it crashed after an hour, well, you didn't get the benefit of a full night's worth of testing. So Z-loop will let it run. If it crashes, it archives off all the information, like all the log files and the VDEVs and the core file, and then it runs it again. So you'll get the benefit of a long-running test overnight, which is when I usually run it, Z-loop, run it overnight. And then you can come back and you have all this wealth of stuff to go debug after you run it. Here's sort of an example, and again, I apologize, you can't see that, but it'll summarize, when you run Z-loop, normally it'll just give you sort of a terse summary of what it did. In this first line, it picked D-RAID, 27 disk, and then the D-RAID, the different, 2 spares, 10 wide with the D-RAID, parity 1. And then that test passed fine. Then we ran RAID Z, 9 disk, parity 3, and it crashed. And so then it archived the disk, all the information, and then it'll just run another test. If people are interested during the hackathon, I could do a Z-test breakout with live debugging. If you ever open a pull request and it says Z-loop failed, and you're like, and what do I do now? I can give you some tips on debugging that. At the end, maybe at the Q&A part, I don't want to risk going on the internet right now, but I'll walk through that later. So why not have more chaos in Z-test? So we have customers that have multiple pools, and a lot of configs now have like an R pool and your data pool. So it makes sense that, hey, if you're going to stress it out, why not stress it out with multiple pools? So it was a great learning exercise of how Z-test works, because I had to like go in there and figure out what it was doing before I made this change. But essentially, it's similar in function. So, but instead of each thread like saying, I'm going to hammer on this pool, on this data set, I'm going to hammer on this pool and these data sets. And I just arbitrarily said, like, the thread count is multiplied by the pool count. So then you're going to kind of get that same stress across multiple pools. Let's see. And then one thing that I added, which I think the default probably would benefit from, is sort of a check the space, because we provision these files with truncate, and so they're sparse. And so, like, yeah, your test is running fine, except all of a sudden your VDEVs, you can't write to them because they get no space back. And I found some interesting crashes in ZFS proper, because it's like, it's not used to getting no space in the middle of trying to write to a disk. So I added that check. So when you say I'm going to run it with multiple pools, or even, without multiple pools, but you're going to do, a DRAID with 50 disks, it'll check, do you have enough space to do that before running the test? That's kind of a nice benefit. There's a few TBDs left on that pull request. Basically, I'm not testing import and export. I'm just doing the classic Z-test test. So like Z-test will open the pool or create a pool at the start of the run, but then it doesn't like export, import. So we have parallel imports, parallel exports now. So it'd be good to just sort of also have a new test that will export and import. And then as far as logging goes, it's confusing without multiple pools, because it's just spewing stuff. And so with multiple pools, it's like, what do we want to do? I thought we could either tag the lines, or maybe even better, have separate logs for each pool. Because when you have to come back and debug, it's like you got to find sort of the needle in the haystack of what went wrong. So there's a pull request open upstream. I'd like to hopefully get some reviewers on that. I think it's a great addition to finding more bugs. I found several already, and so it's kind of a nice thing. And so here's a run and that you can't see. Well, I don't know. Probably can't see that. So it's the same thing, except now in the summary, instead of just saying I have this pool, how many spaces I got out of it, how much I'm using, I added, you can see the summary. So like in this case, I was running it with RAID-Z with 6 disks, parity 1, and then the first pool has 18 disks because, well, they decided to make new top levels a couple times, and there's another one with 12, and so you can see that it's like the tests themselves have variance, and that's going to show up when you run it against multiple pools. Any questions on the multiple pool stuff? Okay. As far as future for Z-test, as I mentioned at the start, there's a lot of things we don't test, so we could potentially add more stuff. One thing that might make sense is Z itself is a user process, so why not spin up Z and, have a way to test Z in the mix. Another interesting issue is that when you run Z-test, it's going to pick things at random.
Some of the time. And
yeah, I think if we spit out the seed or something like that, we could run it again.
yeah, actually have the CI.
What's that?
Have the CI help us determine if this is like a occasional failure, or if this one fails every time, so that much less work that the developer has to do when they're investigating the CI failure.
Yeah, I'm thinking like that's a good idea. Maybe Z-loop, when it fails, it should run it again.
Rerun that same test again, exactly.
And see if it can diverge onto, you know, like, oh, I ran it 3 times and it failed. Like, this is really a bug versus, you know, we see failures that we'll never see again.
Record the seed value of like a log and consistently do the same seed value, you expect it to do the same
Yeah.
things every time.
Yeah, that's what I was hoping, because, yeah, it's just tossing the coin every here and there. So if we could have all the coin tosses be the same, then we have better odds of reproducing it. Yeah.
Just write out config status equivalent of, hey, this is what I'm running.
Yeah. Yeah, that's probably, and if people are interested in doing that in the hackathon, I'd be happy to participate in that.
Is there an upper limit on the number of pools when you for the multi-pool test?
Memory.
Repeat the question.
Yeah, the question is there an upper limit on the number of pools you can test with? Yeah, it's basically disk space. So when you type in the config, the N, and your config, it'll make sure that there's that much free space in the directory you told me. And if there is, it'll run, yeah. So there's no limit, yeah. It's like if you have a terabyte of RAM, you can really go to town. Other ideas of things people would like to see in Z-test? Is anybody interested in send-receive testing in Z-test? What? Okay.
What about encryption?
It tests encryption, but I mean, it just turns it on, and it's like you're running the code pass. But are you thinking of more?
Back into your send and receive, and it's one of the conversations we had earlier, was if you send something that's encrypted, receive it unencrypted, you know, that whole process, that's.
Oh, yeah, like
you
a
know,
raw receive.
Yeah,
okay.
that 6 mesh possibility of how to actually receive things.
That's a good point. Yeah. Other ones?
I'm curious if there's any like in the development of all the fast dedupe code that you guys have developed. Did this? I imagine Z-test found some interesting things. Any stories from any of those test runs? Found something crucial?
Well, it's hard to say because I'm always finding stuff in there.
Yeah. Okay.
But as far as dedupe goes, we do this. Let's see. There's pruning, and then there's what's the other thing? I think it's the prune. Yeah, the pruning. The pruning is interesting because it's like, how do you prune? How do you know what's old and all that? So we keep a histogram, but that's all like hidden magic in there. So what I did for Z-test, it actually prints out the histogram and shows you like how it came about of choosing, you know, what it's gonna eject. So things like that. That's a good use of Z-test. You can actually run the test, but not have to like recompile the kernel with special flags to generate the histogram and all that kind of stuff. So
Cool.
So how can you help out the community here? I would suggest, and I don't know if I convinced you, but just to use it in your day-to-day development of ZFS. It's like it's so easy to run. You can just run it. You can run it off on the side while you're doing other stuff, and it does find bugs. And then if you're going to add a new feature, to the extent it's in that SPA, DMU sort of core part of ZFS, I'd recommend adding a test. It'll exercise your code. And then if you find a bug in Z-test, like in your development, I'm changing this, but every time I run Z-test, it keeps finding this, like open an issue so that we can go, you know, someone in the community can know about it and go chase it down. Because often, you know, with the randomness, how much memory you have, your CPU speed, all these variances, you get different behavior. So some people on their machine, I've seen people have machines that will reproduce a problem, and then I'm go on my machine, I cannot reproduce your problem. And they swear that it's like 100%. So if you can file issues, that'll be helpful. And if you're willing, help us chase some of these down. I know, thank you, Paul. Paul's been doing it. I see occasionally Paul in there chasing down a bug. Because it's annoying when you're trying to do your work and you keep tripping over these bugs. I know when I was finishing up RAID Z expansion, I kept running it, and I was trying to chase down a few known RAID-Z expansion bugs, but I kept encountering all these other ones. So it's nice to get those out of the noise. Ideally, Z-loop and Z-test would run with no issues. That would be the goal. And then we can have high confidence that if it does break, we broke it, basically. Any other questions?
So this is not specifically about Z-test, although Z-test is a part of it, but it's about sort of like the code base in general and quality and passing tests. I feel like over the years there have been a few features that have managed to integrate with testing problems. One of them that caused pain for quite a while was hole birth in ZFS send and receive, where we tried to omit sending holes and then lost birth time information and caused some data corruption in a few cases. Encryption's another one where there are still a bunch of lurking issues with encryption, especially around send receive, but also in general. It feels like we need to have a conversation at some point about how to actually ensure that ZFS is consistently like passing tests and resolving the bugs that we find, and like that you can run Z-test for 24 hours without hitting an issue, and that there aren't known failures in the test suite that could be masking serious bugs. And like how we try to ensure that ZFS stays a best-in-class file system and like stays reliable and performant and does not lose people's data. And so I think encouraging people to use Z-test is a good part of that, but I think we also should have a conversation as a community about like standards for testing and standards for like defects and things like that in new code and in existing code.
Yeah, that would be a good conversation to have with Brian or Tony maybe, but yeah, right now I don't know what the threshold is for like, Z-loop has sort of random failures in there, so do we not require it, or we just say run it, if you run it again, you're going to get a different answer, so.
I think that's the problem. Like, so yeah, it's a fantastic tool, but it's been neglected. And so over the course of years, you know, it would fail, and then we just nobody was really looking at it, so it got ignored. Where like the ZFS test suite, I think probably got more weight just because it's testing that specific functionality, and Z-test being more of a stressor, but it does require us to like kind of spend some time and be like, okay, maybe it's time to go back and invest in it some more so that we can trust it, because I think that's where it's lost favor, you know, amongst developers, is that it's really good at certain things, but oftentimes it crashes, and you're like, it's crashing in code that isn't mine, and I don't have time to go, you know, spending time looking at it. But I think we need to Paul's point.
While I'm waiting for the next question, I'm just going to bring up the web page for the GitHub for ZFS. If you go to the actions page, off to the left, you can see Z-loop there. And this is all, oh, look at that. Somebody broke Z-test. So, sorry, Alexander, looks like Z-test had an issue. So you can click on the Z-loop here, and then you can see, well, I don't know if the internet's going to work here, but I'll just try it. Okay, so this tells me what it was doing. It was running a RAID-Z test when it failed, and then for some reason it didn't dump a core, so I don't know. This one's a little trickier. Often, if you go to the GDB log, it'll show you the backtrace of like what crashed, and that's useful. Sometimes ZDB will crash.
That's a problem.
Let's see if ZDB crashed. Oh. ZDB was busy. ZDB didn't crash. So yeah, this one's a mystery. But often, like if ZDB crashes, then you can just take those VDEVs and run it again until you solve the problem. That's the one nice thing about a ZDB crash here. A Z-test, you can run it again and get completely different coin tosses, and then you're not testing the same exact thing. But sometimes, I've found more often than not, if I just rerun, it'll crash again because I broke something fundamental, and it's like, it's going to tell me. So. Other questions? All right, I'll be available up here if people want to talk about it. And then, like I said, tomorrow, if people would like sort of a hands-on debugging Z-test and or Z-loop, I'll be available for that. Or if someone wants to hack on adding send and receive or some other missing part of Z-test, I'd be happy to help out there as well. All right, thank you.
visibility that scales and get us telemetry.
All right, good afternoon. My name is Sam Atkinson. I'm a software engineer at AWS. And today I'm going to be talking about visibility that scales. I work on the FSX for OpenZFS team. Today we offer a couple of file systems, of these single tenant file systems in AWS, manage them for customers, make a whole bunch of cool automation for them and features and benefits so that they can run their file systems in AWS. So I'm gonna start today by giving a quick overview of like what FSX is for those of you that don't know. A quick overview of our customers and a couple of interesting workloads that are being used on FSX. And then I'm gonna spend most of the time today talking about something that our customers want and a problem that we have with what they want and how we're fixing that with OpenZFS, some challenges with that, some solutions with that, and then we'll wrap it up with some next steps. So just a quick overview on FSX. I spent a bunch of time on this last year, so I'll try to breeze through this. But Amazon FSX it's an AWS service which allows customers to launch, run, and scale feature-rich and performant file systems with a few clicks. We have several different types of file systems today, all of which offer highly available and/or highly durable deployment options, various types of data encryption, and are pretty cost-effective. So just a quick kind of timeline of FSX. We launched in 2018 with support for Windows and Lustre. In 2021, we launched support for NetApp ONTAP and OpenZFS. And then in last year, 2023 and 2024, we added a lot of support for more highly available deployment options, and then cross-file system replication support, send, receive. And so there's obviously a lot missing here. We've done a lot in the last several years, but I just want to show, we've put a lot of investment and a lot of time in expanding what we offer in OpenZFS and bringing more customers to the service and using OpenZFS. So why, back in 2021, did we start offering OpenZFS on FSX? We found a few common customer workloads that were having trouble kind of figuring out what's the optimal file system. For my workload, we have a bunch of file systems in AWS. Why is one not working? Why do we potentially need to introduce another one? And we found that a lot of these customers were using workloads that fell into a couple common categories where high performance databases or source control, source code version control and software builds, ML and AI a little bit, EDA, electronic design automation, some media rendering and transcoding. So these were all workloads that had a couple of common traits. They were usually pretty latency sensitive. They were IOPS intensive. They were looking for some business management capabilities that you'd see in a lot of file systems today, taking snapshots, restoring those snapshots cheaply, and then overall, just being a cost-effective solution that they can take their existing NAS, put it in AWS, and not have to do a whole lot of heavy lifting, to get up and running. So let's talk about I guess what customers love about what we introduced when we started offering OpenZFS and AWS. So I'll start with customer Amdocs, who does the software and services provider for telecommunications and media companies. They do a lot with high-performance databases. They do a lot of database copies. And so they were facing some operational costs and management challenges when creating database copies on their previous storage solution. So they needed instantaneous high-performance copies of these databases, perfect fit for OpenZFS and snapshots and clones and such. And so they were able to switch over to FSX for OpenZFS, reduce their relational database footprint by 60%, reduce their overall data by 5x, and more than double their aggregate throughput. Another customer I'll just quickly talk about is Astera Labs. They're a leader in connectivity solutions that remove performance bottlenecks throughout the data center. They were using a self-managed OpenZFS NFS server, and they were running into a bunch of limits on performance and around total storage. And then by moving to FSX for OpenZFS, they were just able to get sort of an easier setup, a consistent high-performance file system, and access to virtually unlimited storage capacity in AWS. All right, so you've seen two customers here having success with the service, but there's a lot in the weeds. There's things that are missing that customers would like. And so let's talk a little bit about this middle sort of category of things that customers love. These advanced ZFS capabilities. So what are we talking about when we talk about these capabilities? So these capabilities what we're talking about are these interfaces that customers are using. These are the only interfaces that they have to interact with to use FSX for OpenZFS today. So when they're administering their file system, whereas they might have previously used a ZFS CLI command, libzfs, before they're going to be using the Amazon FSX API, SDK, console, et cetera, to do things like create, modify, and delete data sets, scale, provision, throughput, storage, and IOPS. Their workload, they're using NFS like any other NAS that they're coming from. And then they're able to use this container storage interface driver, the CSI driver, to really quickly and easily attach storage to Kubernetes nodes. And then the cool one that we'll focus on today is monitoring. So to understand file system performance and analyze user activity, they're using Amazon CloudWatch metrics, which lets them use a really clean user interface in the AWS Web Console to go and look at what's going on in their file system, where they might have bottlenecks, where they need to scale, et cetera. So what do they want? What's missing here? So in particular, in that administrative category of interfaces, we started to see a common pattern where customers that were isolating like downstream teams or customers within data sets were using user and group quotas within those data sets to limit usage for each of those downstream teams or customers. And so they were often like heavy users of user and group quotas. And so it makes sense they would want to monitor those user and group quotas. And so they often had trouble like understanding user activity or taking proactive action against workload interruptions when they might need to scale storage before they run out of space so that no one's stuck when the file system runs out of storage capacity. And then identifying noisy neighbors so that they weren't blindly scaling up when one or two users was like using more space than they should have. So great, because customers want this quota monitoring, and ZFS has native support for quota monitoring with this ZFS user space command. So what's the issue? So the issue is we might not have a place that it fits perfectly. So we only have these interfaces to work with right now. There's certainly potential to add more, but for now we have these couple of interfaces. And so there's one missing here, which is there's no ZFS CLI, there's no libzfs for customers to work with. So we have a little bit of a challenge. So we have a couple of options. Maybe we put the user group quota utilization in the FSX API. We do, maybe something like this. Possible, but if we lay it out like this, you might see that we could very quickly blow up the size of an API payload. The limits on user and group quotas and the number of users that you might have using your file system is not usually known ahead of time when they're provisioning their file system. And so this list can grow massive, and so in a single request or response, we're totally blowing up the payload size. It's not scalable. We could paginate, but then we're running into TPS limits where if they have upwards of millions of these, we're looking at a lot of TPS being added to our front end, and maybe that's not scalable either. Storing this information also is not cheap. ZFS already does it for us, but we'd have to store it on our own to be able to expose it through our API. So this whole thing, like maybe there are some scaling challenges here. Well, if we don't have other options that will work, like this may end up being the direction we go. We'll see. But it's common for customers to have pretty enormous numbers of users. So scaling issues could be something to think about here. Another option, maybe we use Amazon CloudWatch metrics. It's something they already go to, something they already use to monitor their file system. They can quickly analyze patterns in utilization. They can do some pretty cool stuff with CloudWatch metrics integrations. They could, for example, create alarms that fire when a certain quota is approaching whatever 90% utilization, and then take some action automatically to kick off maybe a storage scaling operation, or notify them, send them an email, that they're a little too close to their threshold. So there's some cool stuff they could do here. And then finally, ZFS tooling, the ZFS user space command. Maybe that's an option too. Maybe we figure out a way to expose that. All right, so we come back to where does it fit? We've looked at these options, and the missing one, which would make the most sense, maybe naively, using like just the ZFS user space command and exposing that, is not here. So why is that not here? So a couple reasons. We're trying to sort of balance these core tenets in these interfaces that we expose. So the reason that we don't, just give them a shell to the file system today is for a couple of reasons here. We're trying to minimize the attack surface, so limiting the interfaces that they have available that we don't today offer, shell access or iSCSI. There's a couple of other protocols. We're trying to maximize parity with libzfs, give them hopefully, an interface to do things like look at zpool iostat, look at the properties of the data set, and then maximize performance. So trying to minimize like the cognitive overhead of, having to think about what super low level tuning do I need to change? When I provision my file system, like they shouldn't have to think about that because we know what hardware we're putting the file system on. We should know where, what a lot of those tunings should be ahead of time. And so if we can take that out of the picture and sort of guarantee to them that, yes, as your workload changes or if the hardware would change, like we're doing our part on our end, changing those so that you don't have to think about it. So enter this high cardinality telemetry problem. So the next best thing that, option that we have for this user and group quota utilization might be the Amazon CloudWatch metrics. That's like it's a really nice system for looking at history and doing automation, adding, little hooks to events that happen when they approach user and group quota utilization thresholds. So let's look at that. So we talked a little bit about the ZFS tooling. This is being requiring shell access, being a pretty big undertaking to mitigate security risks. It's something that we're like looking at doing in the future, but for now it's not something that we're doing immediately, just to keep our sort of security plane as tight as possible. We talked about the API that doesn't scale. So finally, Amazon CloudWatch metrics, what's the problem here? So the way that Amazon CloudWatch will sort of store metrics today is using these dimensions. You can think of it a lot like a database, that every combination of metric and all of its dimensions is stored and indexed independently. So when you would store a single data point for a single user's quota utilization on a particular volume or data set, you have now inserted one row into your database that's going to be indexed totally separately from everything else. So basically, when you have many of these combinations, querying them is super inefficient and super costly. So a common example here, a totally reasonable thing for customers to do, have 10 file systems, say, have 500 data sets, have 500 users on each data set. You're now looking at 5 million unique metrics. And you can't query 5 million unique metrics with one API request. You need a lot of API requests to get that. So it's not efficient. It's not what they're looking for. So what other options do we have? So platforms and services exist for this kind of high cardinality telemetry. We already have just tons and tons of combinations of dimensions that are stored independently, but they're inherently expensive. They often trade off costs with short retainment restrictions, but they're still super costly because you're storing and indexing data at a really highly granular kind of way. So if you had if a customer had 1 million data sets, how do they make sense of the state of the world? How are they looking at a single user that has usage across all of their 1 million data sets? Are they querying 1 million? Are they making an API request 1 million times and then adding that up? Is that something that they should have to do? Probably not. And then if we're managing 1 million file systems with 1 million volumes or data sets each, can we efficiently scale? So how do we balance these? So let's talk about the solution that we've been looking at most closely. So we started asking customers, do you really want this, this expensive quota utilization history forever? Is it useful to have it forever? What do your access patterns look like? And we started finding that they usually involved searching for something either at some period, at some repeated period, or when some event happens. So when, a customer would report, when a customer's user would report, hey, I'm getting space here, what's going on? Then they're going and looking at what's the quota utilization and what can I do about it? Or maybe they're running, once a day, they're doing an aggregate, look at all of the data sets, looking at every team's usage, at every customer's usage, where either some quota limit is being approached, the file system ran out of storage, or they're just looking at usage across teams or projects. So they don't need it forever. So this is granular data. It's already stored efficiently in OpenZFS. The FSX API and CloudWatch metrics maybe don't meet customers' requirements. Is there something that we can do in the data plane with that third interface, with the data plane interface? And what if customers could access metadata in the file system itself across NFS? So this is something we looked at last year during the hackathon and had little success at that time, but we have made a lot of progress on that this year. So we looked at using the .zfs directory, the ZFS control directory, to add in more of these pseudo files. So doing having a procfs almost in .zfs. So there's precedent here, the ZFS snapshots and I think it's shares, thank you. Directories are already in there where you can go and look at your snapshots and in a read-only way. So there's precedent there. It's zero cost because we already have the ZFS user space command. It'll go and use libzfs and look up in a really efficient way, show me what all of the usage is across different users. It's instant and it's always up to date. The instant and always up to date are two unsolvable problems if we use any other interface to do this. So there's there's a lot of benefits here. So we spent some time working on this last year. There's a pull request up to expose this information in the way that you see here, but it's not. There's some complications that we'll talk about. So Let's take a look at some of these properties of these pseudo files. So like I said, it's similar to procfs. It uses the same interface as a lot of procfs files, the Linux sec file interface. So you'll see here that when we stat this file, it looks like it's 0 size, and that's nice because when we go and read the file, we'll just at runtime go and fetch everything from ZFS and return return the whole list of users and groups in real time. It's great, no storage cost. But what's the issue here? So like I said, the size looks like it's 0. So the challenge here is with NFS. The NFS client today, and at least in Linux, and actually this is the case in a lot of NFS client implementations, has this optimization that you see here, where if it will always stat the file first, and if it sees that the length of the file is 0, it will optimize out a read, and it will just give you an empty page. So not ideal here. So a couple questions immediately arise. Can we change the Linux NFS client implementation? Maybe. Should we change the Linux NFS client implementation? Maybe. If we did change the implementation, what are the hazards? What are the mitigations? Should the pseudo file contents allowed to be cached? If it's a procfs-like thing, maybe not. And then we spoke a little bit with the Linux NFS client maintainers. They were like, it makes total sense. If you use ODirect, this is a perfect fit because you're not putting anything in the page cache, and you're treating it exactly like you would have a procfs file. So if you force your clients to use ODirect to read these, then fine. You can make that change. So great. So we can change the Linux NFS client. We would unblock our customers. It might open other doors to other pseudo files, procfs-like things. But it requires ODirect, so a lot of tools won't work out of the box. Customers will try to read the file, they'll have no idea why it's returning nothing, and that stinks. It will take a long time to reach our customers because it's a kernel change. And then there's the whole unsolved problem of every other client out there, BSD, macOS, Windows, clients that would need to change too. So what other options do we have? We could maybe vend a tool. We could maybe change the file layout to make this work. Maybe change the file size to make this work. So let's look at some of those. So one option is we could vend a tool. Instead of letting the NFS client driver issue the read, we could issue the NFS read ourselves from a tool. So we could read beyond the inode length. There's no need for any driver changes, any kernel changes in Linux or any other client. It's a similar way to how Oracle Direct NFS works. That the read is issued directly from user space. And then, that all sounds great, but it requires some NFS client code in the tool, which is not ideal. We have to maintain this tool, vend this tool. If we have, NFS code now in it, it's a lot more overhead to maintain. So you can kind of see here how this works. It's kind of reversed, but the Linux client would create the session, do the mount, so it would look like a regular mount. You could still treat the NFS filer like a regular NFS filer, but using this new tool, it would be issuing extra, put file handle and read requests to do the read beyond the 0 length of the file. So that's great, but it has some challenges. Another option is we can change the layout. So the real problem here is, of course, that the 0 length file read is optimized out. So what if the files aren't 0 length? Do we have some upper bound we can put on the file length? So maybe. So with the existing layout, I don't know if you noticed that each user and group would be on its own line. And so if you have millions of users and groups, the file is millions of lines long. So maybe there's not a nice upper bound we can put on that. If you're of course then going to run into use after access issues where you like look at the size of the file and it's changed because another user has written something. So there's challenges with putting an upper bound on that. So how else can we do this? So we could change the layout completely and have maybe one pseudo file per user or per group. And then we have a really nice upper bound we can put on each one of those pseudo files. So something like you see here where there could be n number of user or group pseudo files in this directory, and then each one has an upper bound of whatever would be, say 1K. And your clients can all read that, they all can understand that, and all their tools will work, so great. The challenges with this are it's great, it's O of 1 to get utilization for one user, but a lot of these access patterns are not really, they need more than that. They need a lot of times to look at the utilization for all the users because they're trying to search for which user has the highest. What's the noisy neighbor? Or what do I need to look out for in the next 2 days before I scale, that kind of thing. So it's not great for those because you're doing many NFS requests just to find that user. The other challenge here is that when we have n number of these pseudo files, we need to decide how to allocate inode numbers to each one of them. So today in the ZFS control directory, each one of these files, each one of these inodes has its hard-coded inode number way high at the upper range of what we can support. And so it's really easy to add one or two. It's really easy to add just a user space file, just a group space file, and we add 2 entries to this list, call it a day. But if we have a bunch of them, now we need a way to allocate inode numbers for this control directory, maybe keep them around, maybe not. And so it's a much bigger lift to go and change how we would allocate these inode numbers. So what's next? We have a lot of options here. Next is talking to customers, trying to find the option that fits best. It's not the end of the road by any means here. So we've been talking to some customers. We'll probably end up iterating on the pull request a little bit more, and trying to find an option that sort of works best for everyone. And then it's also not the end of the road, I think, for this kind of pattern in general. In terms of what we can use this pseudo interface for. There's a lot more you could do with read-only metadata, letting customers see argstats and zpolyostat live, maybe mutating things, maybe changing their user and group quotas, and then changing maybe advanced tunables that they currently can't today for those that want a lot more depth in the way that they configure their file system. So that's kind of what's next, and I'd love to hear any thoughts or suggestions on why you'd like to see us go this path or that path, or any other ideas you have. We'd love to hear. Yeah, that's pretty much it. So, any questions?
Have you considered modifying for the control directory the stat so that it would return the actual size? Like you'd end up building the list twice, but it's not something you expect somebody's doing once a second, right?
Yeah, we could do that. I think our concern there was the time of use, time of check thing. It is something we could do though.
Do you know how the client responds if you just say the file's a kilobyte, but if they keep reading, it keeps returning stuff? Like if you don't return EOF, like cat would keep reading, right?
This may not be the case for other clients, but the Linux NFS client will stop after 1K.
Helpful.
Yeah.
Is the data just sort of the point in point-in-time snapshot of information at that point of time of the snap? Is it correlated one-to-one with a snapshot of the data set?
It's not correlated with a snapshot. So it's the live result of the current user and group quota utilization and settings for that data set, like at time of access.
Got it.
So it's not on a particular snapshot.
It's the real time.
Yeah.
And are you pushing all the data into like InfluxDB, so you've got history that way?
So that's potentially something we could do or customers could do.
Yeah.
So like not every customer needs the history, and so those that do, maybe it's worth the cost to do that. But we found that a bunch of them don't care and don't want that added cost.
Right. Yeah. It also seems like, in a way, maybe trying to push too much into NFS, and that you should just really have an API for it,
Right.
that they can call, and then you could do creative things,
Right.
and do faster lookups and have it cached versus. But I think it's super cool that you're putting the data in there. I think that's super handy that you can get fast access to the quota information. So
Yeah.
I think it's super cool.
Yeah. Thanks.
Have you guys looked at, maybe instead of being able to get all the data, what if it's like reports, where it's like, show me the top 5, where you can limit and you have a better idea of like what's going to be presented, so you're processing it kind of on the back end.
Yeah.
And then you kind of have like a reports directory, and you can kind of build from that.
Right. Yeah, like a report that would have an upper bound on
Yeah.
on size that would make this all a lot easier. We actually haven't looked closely at doing that. That's an interesting idea that I think some of our customers would be quite interested in. Yeah, thanks for the suggestion.
And kind of maybe on the same vein, what about padding out each row to be a fixed length? So if every row is padded out with just spaces at the end on like an extra comma separated field, so that everyone was 64 bytes, then you would know, there are X users, therefore the file will be that times +1 for the header times 64.
The tricky part with that is just that if a user
writes something in the meantime.
If a new user writes something, yeah, because it's
Yeah.
not just the users that have quotas, it's all users.
Right.
So any new user writing anything would change the size.
Although the quota stats only get updated once per transaction group, so they're only going to change once every 5 seconds-ish. So maybe
Yeah.
the whole is small
Yeah,
enough, but
Yeah, we can get.
then
creative
you're
there.
also, you're making somebody read a lot of space characters for
yeah,
no reason, right?
Yeah.
I've got one question from YouTube. This is from Jan. Actually, no, it's good. What if you return the map size possible and return the EOF early, as if the file had been truncated before step 3?
Yeah. So I'm not sure if that question came through, but it was if we returned to EOF before the end, as if the file were truncated before the read. We could do that. The risky part with that, I think, is just the timing that if a user would write, within that period of time. Now you're kind of not.
What's your target accuracy for this?
Yeah. If we're
Looking at instant, or do I need a summary
yeah.
on an hourly basis?
So some customers I know have not really expressed the need for the real time, and just like an hourly update would be fine. The thought, I think, was that if we take this route and we'd say that this is real time, which is one of the like huge selling points of it over the API or CloudWatch, that if we say that it's real time and then we're deliberately sometimes pulling things out, that's iffy. It's something we've looked at, but kind of ruled out because of that reason.
Next question. Do you consider making all file system properties readable through pseudo files?
That's not something any of our customers have asked for, but I think that would be a really cool thing to do, and it would be pretty easy to do, just with what we've done here. We might run into issues with the inode allocation problem, but if we have to solve that problem anyway, then great.
And then the last part was, could you provide a pseudo file with a specific
We could do that. Yeah, I think if I remember correctly, I think like ZFS User Space will already do this. I could be wrong there, but whatever the order we pull it out of, I think that's all stored in the ZAP. Whatever order we pull it out of there is the order that we would return it here, and I think that's already sorted today. Is it not?
I think it's sorted based on.
Is it by? Oh, by entry?
Yeah.
I see. I see.
Like numerically increasing.
Okay. So then we could look at doing that. We have not looked at doing that.
Have you experimented with this? Like in your example case where there's a very large number of users, if you're reading the file kind of in chunks, as the client would do, like what happens if the results change while you're in the, like you've seeked 2 megabytes into this file and now the results are different?
Yeah, so that it's all based on how ZFS like paginates through the ZAP. It's the same way. It's the same behavior as if that happened when you used ZFS user space or group space. So the results could change, then probably will change, like halfway through, but it's always the most real-time result for that particular user or group.
Well, I just meant with the sequential file mechanism from
Yeah.
Linux, if we're seeking and now the 64K barrier where we're reading in chunks doesn't land in the middle of a line. Could it like mess up the format where you're missing a new line because you
or even
read
if
half the record on the previous read?
Even if it does, I think you have a problem with if I just do a read starting from offset 1 billion.
Yeah.
How do you know which user's line starts at offset 1 billion? Like, do you have to generate the whole report up to that offset to then give them that section of it?
If I remember correctly, I think that's how the seek file interface works, is that it will have to iterate through from the beginning. I think
that has a couple of problems. One, obviously now you have it's O of n squared
instead
of O of n, which is probably going to be very bad for large, if you have a large number of users. The other problem is you might have garbled output. So like imagine that I'm getting it in 1 kilobyte chunks. So I get the first kilobyte, then now I'm going to get the second kilobyte. If nothing has changed, then it's going to work right. It'll just be slow. But then imagine if like a new user came in, or even an existing user's space usage increased or decreased such that the number of digits is more or less. So now the second kilobyte, I'm returning them the second kilobyte of the current report.
Yeah.
But they have the first kilobyte of the first report from a second ago.
Yep.
And the second kilobyte of the second report.
Yeah.
Then like those don't necessarily line up.
Right.
Right. You could have a repeated digit or a missing digit, and then you think that somebody's usage is 10x or 1/10 of what it really is.
I think this is. I mean, I don't know how you would avoid this downfall with like an interface like seek file, but I believe that's I don't know if you'd call it a flaw, but a behavior of seek file in any of these interfaces.
Yeah, I think so. I mean, I think that having a dynamic file, like essentially you're like modifying the file while somebody's reading through it, and you're modifying it by like shifting data around within it.
Right.
So I don't think it's possible to get a consistent result.
Yeah.
I think you need to either dictate, like you must read the entire thing with one operation. Like you cannot seek to non-zero value. Right? You can only read starting at offset 0. We'll give you the report up to that point, and if there's more report after that, then just do another read.
Right.
Right.
Yeah. So I mean, potentially, like an argument for venting a tool, like even if
like inventing a tool that would have this behavior where it's like, well, it says that the file is a terabyte long, but what I'm going to do is like read the first kilobyte. Oh, there's more stuff after that. Read 2 kilobytes. Read 4 kilobytes. Read 8 kilobytes until I've gotten like the whole thing in one read operation.
Yep.
Or you have to go down the route of having the one file per user interface.
Yeah.
But
Yeah.
does the Seek file interface do something for this? Because we would have the same problem with like the debug message kstat, right?
Yeah, I think that's true. I think that
But I don't know how different it is when you're doing it over NFS.
I think that the debug message kstat does have this problem.
Oh, okay.
It's just like, yeah, you put up with it. It's debugging.
Yeah, it's for debugging, so it's okay.
But it might be reasonable to say, like, I mean, think about your problem of like how many users do you really need to support,
Right,
and
right.
how big could the maximum report size really be? And maybe that's like 10 megabytes. Okay, so the pseudo file length is 10 megabytes, and you do it with one 10 megabyte read. That might be okay.
Yeah, it's true. Yeah, I think that's probably somewhere where we need a little bit more data on, like, realistically for these customers. I mean, what are we talking about here? Are we talking about millions of users, really?
Yeah.
Yeah.
You'll have to repeat this one, just 'cause next time. Why not vend a tool, NFS utils, can also be a wrapper that you can ZFS client to and can execute from pricing?
Yeah, that'd be a cool thing. If on your client you could like run ZFS user space and it would go through this tool. That would be super cool. Maybe something down the road. I hadn't thought about that either. Any other questions? All right, thanks a lot.
Awesome. Yeah, I thought it might be good to talk a little bit about the next release of OpenZFS that we're putting out. So this is going to be a little bit of a different talk, maybe than what we've had so far, since it's looking at what we did over the last year rather than what we want to do. But I thought it'd be interesting to put it together and give everybody an update. So we were just talking in the parking lot about how much current activity and churn there is in the OpenZFS tree. So not everybody probably knows what happened in the last month and got integrated. So it was kind of interesting to go back and review what's been done and what's interesting. So this won't be an exhaustive list of changes that were made, but I tried to pick out the most interesting stuff or the most noteworthy, or maybe whatever just struck my fancy at the time. So where are we in the release cycle at the moment? So for OpenZFS, we put out major releases about we shoot for every year. It ends up being more like every year and a half, something like that in practice. So we're coming up on putting out the 2.3 release now. So where are we at in that process? About 2 weeks ago, 3 weeks ago, I don't know, something like that, maybe a month ago, I cut the official release branch for 2.3. So that means we're feature complete at this point. There won't be any more major additions to the branch. Any new features are eligible to be merged to master, but we won't be picking any more really big disruptive changes into the release branch. As part of that, we've got the usual process of doing things like bumping the library version. For those who aren't familiar, part of the process we go through here is within a major release branch, right, we have a stable ABI that we check. So within the 2.2 series, right, libzfs, those interfaces won't change. But we do allow them to change in the master branch while we get ready for the next major release. So when the 2.3 branch gets cut, which it just did, we bump the library versions. I think this might have caught a couple people off guard, actually, when it happened this time. But that's typically when we do it. So now we've established new stable library versions for libzfs. Those will be stable for the length of the 2.3 release, which is, at least for typically 2 years, we'll maintain the 2.3 release. I guess one other thing folks might not know about those release versions is the way that we've always structured the RPMs, at least for the last couple releases, that you can install multiple versions of those APIs concurrently, right? So you should be able to install the headers for like version 5 libzfs 5 and libzfs 6 concurrently on the system. So those have been stabilized now. So at this point, we're just trying to wrap up any remaining issues in the release branch before tagging a major release. We have some known issues we need to work through still. We're working on it. We will integrate those into a couple more release candidates before the final tag. And then the usual bits involved in putting together a release, right? We've got some packaging updates we need to test out, documentation, and then here's my call for testing for everybody, right? So we've got 2 release candidates under our belt so far. So there's a 2.3 RC2 available now for folks to download and start kicking the tires. A lot of good issues have come out of that we've fixed. We're right now staging a new PR for RC3. The link is here. You can find it in GitHub, right? But here's where I've been accumulating backports for the master branch for additional fixes to pull into a 2.3 RC3. Hopefully we won't have too many more RCs, and then we'll put out our final 2.3 release. So I think that's a pretty standard process, but that's where we're in the cycle at the moment. So like I mentioned earlier, typically we shoot to put out a release every 12 months. In practice, that doesn't often happen. Usually it's more like 15 months to 18 months, right? So we're about 15 months for the 2.3 release cycle. Activity looked about the same to me compared to prior releases. We had about 900 commits between the 2.2 release and the 2.3 release, which was about what we usually see, and over 100 contributors, which was great. So thank you to everybody for this release cycle who contributed stuff. It's great to see the continued contributions from folks. And with that, what I wanted to do was probably go through some of the major features and interesting features that we've integrated over the last, 15 months or so. So I'm not going to do a deep dive on all of these features. It's going to be kind of a whirlwind tour of what went in. but there are, talks at previous development summits talking about all of these things, or at least most of them. So I'd refer you back to them if you really want to know the details. So with that, let's see where we're at. So first one, all right, this one was merged almost right after 2.2 was tagged, and it's been soaking in the tree for almost a year now. So this is the RAID Z expansion work. This turned out, I would say, really well, and we've had some good reports that everything's working well with it. It's had a lot of testing, so it's in good shape. This is probably one of our most widely requested features, so I'm really happy to see it finally get integrated. And it has been under development for a long time, I think, as everybody here knows, right? This was a long time coming and a big lift, but I think everybody will be happy to see it finally be here. So just to refresh your memories, right, some of the high-level design details for RAID Z expansion, right? It works with RAID Z 1, 2, and 3. It does not work with DRAID yet. There were provisions put in DRAID originally when it was merged, but none of that's been implemented yet. So you can't use RAID Z expansion for a DRAID pool, but that would be a cool thing to look at in the future. You can expand a pool multiple times, right? These are all things that have been talked about in the past, right? Reflow data retains its previous data to parity ratio. Pre-expansion, and then post-expansion too, the ratio doesn't change. When you add another drive, you get the new data to parity ratio. So that can complicate things like free space reporting a little bit, which I've heard we've had some reports of. But that's working as intended, right? One thing you don't get with RAID Z expansion, though, is you can't change the parity level. I've seen this come up in a bunch of discussion threads too about people wanting this functionality, but that's a lot harder, and that's not something that's supported as part of the RAID Z expansion. So RAID Z expansion is in 2.3. Another huge addition that was merged in the last, 6 months, something like that, that Clara and IX Systems worked on a ton. And this was another big lift, was improving dedupe, right? So the fast dedupe feature has now been merged. This was a nice overhaul of the deduplication system in OpenZFS, right? It's designed to coexist with the previous implementation, and really from 50,000 feet, like what it ended up being, was a major collection of performance improvements to the existing implementation, right? Looking at a lot of areas where the current dedupe system fell a little bit short and needed some improvements. So I think Alan gave a talk, I think it was last year, about the improvements in this. So I refer you back to that for the details. But the gist is, it tried to address all the shortcomings we had seen, right? So make sure your dedupe table fits in RAM where possible, right? So things are quick to look up, or a dedicated flash device failing that. Move it to a log structured format, right? So we can do efficient updates rather than doing tons of read, modify writes to the dedupe table. The pruning functionality was mentioned earlier, right? So you're able to prune entries from the dedupe table, just a whole collection of general improvements here for deduplication. So actually one of the other interesting things that I thought that came out of this too was just not the dedupe functionality, but the ability to add a generic prefetch command to ZFS, which I'd like to see. So the only thing that makes use of that now, there's now a zpool prefetch you can issue. And right now you can only let you prefetch the DDT, but it's something we could build on long term if you want to start being able to pull in other functionality. So you want to prefetch a file or the metadata for a file or metaslabs, right? It provides an interface for us to build on where we can pull in perhaps more information if the user knows they need it. So DirectIO. DirectIO is probably the other really big feature that finally got merged. So this is another one that's been under development for years and years and years. I think since at least 2018, it's been being worked on. So DirectIO addresses a lot of the issues that we've seen and probably came up before in talks earlier today about NVMe devices. So for those, we've got a developer group here, but for those not familiar, ODirect basically lets you bypass the cache is the general mechanism. So For ZFS, that means we bypass the arc for reads and writes whenever possible. It works just like normal ODirect. You pass the ODirect flag to open, and you've got the usual constraints. So I/O needs to be page aligned to be issued down the stack. Otherwise, it fails with an error saying you have to page align your I/O. ODirect's desirable for a variety of use cases, right? Again, some of them were mentioned earlier, like databases in particular often implement their own caching mechanisms. It makes sense to bypass the cache in that case for direct I/O, or cases where the data is only read once or read or written once, and there's no point in actually caching it in the arc, right? In those cases, it may make sense to bypass the cache as well. Or, in particular, for really low latency devices, like we heard earlier, where just manipulating the data and processing it can add significant latencies to the I/O times. So being able to bypass the arc can be a significant win there. One of the things that motivated us to do this originally was that we found that for when you have lots of NVMe devices in a pool and they're high performing, just the copies in and out of the arc can limit performance. So just the copies alone limit things. So the way that this works, right, is with the direct I/O patches in ZFS, the user pages get directly mapped into the kernel, and then we do as much I/O as possible directly with those user pages. So they get mapped right down into the I/O pipeline, and we do I/O on that to avoid copies. Obviously, there's some cases where you can't avoid copies, right? So if you have to do any kind of compression or encryption or the calculation of the parity blocks, right, you're going to have to for compression and encryption in particular, right, you have to copy the data because you're manipulating it. And then, for RAID-Z parity columns, right, we have had to read the data and calculate the parity. So there's costs there. But the idea is to touch the data as little as possible. The data is still checksummed, right, so you still keep all of those guarantees. So we do have to process it or touch all those pages to calculate the checksums, but it's kept to a minimum. One of the other design decisions we made long ago with direct I/O, which complicated things significantly in our implementation, right, was that we always wanted to be coherent between if you mixed buffered I/O and direct I/O. A lot of file systems don't work this way, and if you're mixing and matching buffered I/O and direct I/O, you won't necessarily see a coherent view of the file. You'll end up bypassing the buffer cache. For ZFS, we wanted that to always be coherent. So even if you're doing crazy stuff that no application should reasonably do, right, and mixing your buffered and your direct I/O, you should get a coherent view of the file. So that means sometimes we have to invalidate pages that are in the arc, right, or we have to pull pages into the arc if they use that interface instead, just to make sure that we get a coherent view of the file. And one other thing that was added here is a new extension to the zpool status command, where you can see not just errors that are introduced. Let me go back. So like I mentioned before, we're operating directly on the user pages, which means that the users have access to those pages. They can modify them, right? We're not copying the data directly into the arc. And we want to be able to tell the difference between if the user modified a page, and that's why the checksum fails on it, or there's another issue there. And we want to report those independently of checksum errors in the pool. So there's a new column that was added to show data verification errors that indicate you gave a buffer to direct I/O, and it changed before it actually hit disk, right? The user did something to it. The checksum's not wrong. Well, it is wrong, but it's because the buffer changed. And that was actually very, very interesting because we found a bunch of cases with badly behaving software that tend to do that, it turns out, right? And it was causing checksum errors in the ZFS code because it was detecting that the user code was manipulating the buffer when it shouldn't, right? So those are now detected. Code has been added to ZFS to find that, and if it does detect that you're messing with the buffers, it will typically fall back to reading or writing through the arc, right, to give you a coherent block written to disk, so when you come back and read it later, the checksums are good. So that was a big lift. That was recently integrated for the 2.3 release. So those were the three, probably the big major features that went into 2.3 that I think people have seen before and people are aware of. But in addition to that, we had a ton of nice to have stuff that just went in with maybe a little less hoopla associated with it. JSON output for most common commands. Yes. So maybe this is actually more desired than RAID Z expansion. Because this is certainly a long time in coming, right? And in fact, I forgot about it myself and forgot to add it to the initial draft of the release notes, right? But this is a big one, right? So JSON's been added to probably the most common commands now in ZFS. So things like zpool status, zpool list, zpool get, those commands all now take a JSON flag and give you structured JSON out for them. I think personally there's a lot of opportunity to expand this, right? We didn't enable every command, but you can imagine having zpool iostat or zpool history give you kind of more structured output in JSON for those commands. So we can get away from like scraping the CLI output, which I'm sure everyone hates that. Yeah, that's. So some interesting discussions did come out of that. You'll also see there's a couple flags that went in with the JSON output. I guess it depends on your libraries and how they interpret JSON, but some of them interpret integers and strings in the JSON output, and depending on the libraries you're using to parse it, they may interpret it differently. So there's an option there to provide output either as integers that aren't quoted, or like have all the integers be quoted in the JSON output so they appear as strings. There's a flag for that. There are also some use cases where there's like an alternate format where it'll collapse the hierarchy of VDEVs into like more of a list rather than a hierarchy, because it just makes it easier to iterate over the JSON if you don't have a hierarchy there. Again, optional flag, but nice to have stuff. I'm hopeful, like I said, we can build on this as people start using it and finding spots where it either needs to be extended or new commands need to be enabled. But yeah, this will be nice to have. Another nice to have that was recently merged too was long file name and directory support. So this is something that's maybe not as useful if you're using the file system directly like on Linux or FreeBSD, but if you're using it through something like a Samba share, right, or you're embedding Unicode characters or those kind of things, you actually run up against that. The previous limit was 256 characters. You could actually run into that quicker than you'd expect, depending on your file names. So that's now been extended to almost a kilobyte, right? And this is controlled with a long data set property that's been attached to all the data sets. By default, it's disabled, but you can enable it as needed. If this is a use case you have, or you're using it for like an NFS or Samba filer, you can turn it on. For the moment, it's a Linux-only feature, not because ZFS is limited in this way, but apparently we ran into some issues in the FreeBSD VFS layer that imposed some limits. Those can be worked on and improved, I'm sure, but at the moment, you can only get the longer file names with Linux. So we have some more nice to have features, right? So .zfs snapshot directories we were talking about earlier, right? Historically, this has been controlled by the snapdir property for snapshots in particular under there, right? And it can be set to either visible or hidden, and it would prevent traversal into the snapshot directory if it was hidden, not because you couldn't traverse in there, but just because it wasn't reported in the directory or dirents list, right? Or it can be visible and you can see it. Well, there are cases where it probably makes sense to actually be able to disable it entirely, and this wasn't possible. So like say you've got a snapshot that you really don't want to be accessible anymore because it was taken at an unfortunate moment in time, right? So turn it off. So you won't be able to traverse into any of those snapshots until you fix it up or delete it, right? So it's a nice additional administrative control that's finally there now. So this was added just as another option to the snapdir property, and that was possible because of some additional work that was done in 2.2 to let us like properly be able to extend existing data set properties with new values. So that was a nice bit of work to dovetail on that. Additionally, I don't know how many people use redaction snapshots, right? But there was previously a limit there of 36 redaction snapshots. Paul did some work there to allow those to spill into a spill block, so we can do more of those now. I don't know exactly what the new limit is, but I imagine it's quite large. Yeah, it sounds about right. I mean, you had hundreds of bytes, and now you have kilobytes, so right, yeah. So anyway, large enough you shouldn't hit it. Other nice to have things, parallel pool import and export, right? I guess that's a popular one too. So not so important if you've only got one pool on a system, but if you have a lot of pools on your system, then they were previously serialized, right? And they had no particular reason to be, right? They could be done in parallel. And now they are. So zpool import-a and export-a will fully parallelize the pool import and export. So if you've got a lot of pools, it should speed up, startup and shutdown times if those are your use cases. Even more nice to have features, right? So there's been a lot of these items that people have been working on that maybe haven't gotten quite as much visibility. And some of these, I should add, I think on this list too, may have been backported to the 2.2 release too. They went into the master code, but they were nice to have things. They didn't break any of the library APIs or change them in ways, so we were able to backport them cleanly. So the first one here is one of my favorites, personally. It seems like a little thing, but on the systems I work on, they're typically D-RAID pools and they have hundreds of devices. And when you run zpool status, 100 devices is too many to see the output when you're looking for something that goes wrong, right? So you can now use zpool status-e and it will show you any VDEVs and only those VDEVs and their parents, right, that are unhealthy, right? So you can see, like, okay, this one's, and by unhealthy here we mean like something not in an online state, right? It's been removed, it's been faulted, there's read share errors, there's write errors, checksum errors. There's something wrong with the VDEV that you should really look at, right? And this has been particularly nice for our setups because we have a lot of pools over a lot of nodes, they have a lot of disks, and being able to eyeball them in a reasonable way has been very helpful. So I know this one was backported and I use it a lot. Another nice feature for those of you who have enclosures where you can like independently power cycle the slots on the enclosure side, the zpool commands were updated. Zpool online and offline now take a power flag. So you can not just power cycle the disk in the slot, right? But you can actually power cycle the slot directly of the enclosure, as long as your enclosure supports the SES driver, right? So it's been written for Linux, and it relies on the generic SES driver in Linux. Could be expanded for FreeBSD if someone wants to do that work. Like all the hooks are there, they're just disabled at the moment. I'm not quite, I would assume FreeBSD has an equivalent of this. It just needs to be wired up. But this is a nice improvement too, because often we've seen drives that act up and you just want to, you just want to power off the drive, right? And get it off the bus. Along with that, we've had a bunch of improvements Don's been working on and a few other people for the Z, which have been really nice. Like part of this work, again, was powering off the enclosures slots when faulting a disk. This is kind of dovetails again with the zpool online offline work for the slots, right? Often we'll have a drive act up and you just want to power it off. And in fact, we want that to be the default behavior for any drive that acts up in the system. So we've configured our systems this way now. So when you fault the drive, it gets faulted and then the slot just gets turned off. So it can't act up anymore. Depending on your enclosure, you may have to turn it back on, but we found with a lot of modern enclosures at least, like when you put a new drive back in the slot, it'll automatically power it back up. So typically this is very nice for maintenance. It just turns off the slot, takes out of action, and you put a new drive in, it spins it up, kicks off the replacement automatically. That's great. Slow disk I/O diagnosis. This has been improved considerably, so we get slow I/Os and can act on those. I personally think there's a lot of good work to be done here still, right? We track a lot of information about the individual drives and could do a better job of identifying particular drives, like in a similar population of drives, this one's behaving different than the others, right? So it's just slower for whatever reason. It's not reporting errors. It's just slower. And you might want to log slow I/O errors for that and fault it. That's something to look at longer term. This change doesn't exactly do that, but it does put in place some of the groundwork for allowing that kind of thing and better reporting really slow drive behavior. And here, really slow means like I haven't serviced an I/O in 30 seconds, right? I submitted it down and it's just gone out to lunch. Additional changes to like consider disk peers when you're faulting a drive to determine if like really is that drive the problem or is it something all on the same bus, right? And not take any action if it's clearly not this individual drive that's causing the problem, but something more systemic. And then with the PreviDev zaps, right? Now we can do things, and this code was backported too, for like individual read, write, and check some error thresholds for faulting in the Z. And you can set those at the leaf level or the top level leaf. These are all really nice improvements, I think, to the management functionality that we keep building out, and it keeps getting better. And I think there's still room for improvement, but it's gotten pretty nice at this point. On the developer front, we've had a bunch of quality life improvements. Rob Norris, in particular, should be credited for like a ton of this work. He has spent a huge amount of time clearly improving things for all of us developer folk, right? In particular, the user space debugging, there's been some cool new improvements, right? Just in what gets reported when you hit an assertion or in one of the tools, right? So things like thread names are now visible in the process. The stack dumps now include like better back traces, and very recently it'll dump the registers too for the stack. So when something happens, you have enough information to actually go dig into it and see what went wrong. Little things like the asserts were not serialized before. So if you hit 2 asserts in different threads, they get all mangled together and you couldn't tell what happened, right? So a nice set of quality of life, like I say, improvements for these things. Better task queue stats were part of that too. Previously, we did have K-stats for the task queues, but in practice, they weren't very useful. Now you've got much more visibility into like all of the task queues, which ZFS is using internally. There's an entry, a K-stat entry for each of them, and some high-level stats and some aggregate stats for its behavior, and a high-level summary of like most of the unique, or most interesting, I should say, task queues in the system. So this has been really helpful just to get an idea of what's going on and just surface more visibility. Related to this, I'd personally love to see some more visibility into the pipeline for ZFS, right? And you could imagine doing something similar with K-stat entries for that, so you could see a better what's going on in there. We've also dropped support in 2.3 for really ancient kernels. So I know people who have submitted patches have struggled with this for a while. Like we've always supported back to basically the last supported rel release is where we've kind of arbitrarily drawn the line. And that meant some really ancient kernels needed to have support. So if you're submitting a patch, often you'd have to go and add compatibility code for a kernel that was, 3 years old, 4 years old, right? Who's running this thing still? But we do have a lot of sites that run the old enterprise distributions, and they tend to ship with old kernels, so it was important. The good news here is we were based on a minimum requirement of RHEL 7, which has now been end of life, so yay. So we were able to move the minimum kernel version here forward to what's in RHEL 8, which is 4.18, a 4.18 kernel basically, a heavily patched 4.18 kernel, which doesn't resemble the 4.18 kernel in practice too much, but it's based on 4.18 in reality, right? And the upside of that was we got to shed a ton of compatibility code that was just a burden to maintain, right? So as part of that, we also bumped the FreeBSD release version too. To anything older than the FreeBSD 13, we shed that code too. So that was a nice win in terms of simplifying the code base and not having to go back and figure out how something worked in a kernel from 6 years ago or whatever. And this was kind of a nice thing too, right? For those of us who try to build it against bleeding edge kernels, right? We've for a long time now had a minimum and a maximum supported kernel version in the meta file in the top level ZFS directory to control like which kernels we build against and we actually try to build against. Just because we want to make sure that you're testing against a kernel that we've tried, we think it's supported, it works, it passes all the tests. But we've always got people who a new kernel comes out and that day they're like, I want to run ZFS against the kernel that came out yesterday, right? And we have not had time to go through and update and vet it and make sure everything's working correctly. But now it will still fail the build by default, but there's a nice configure option you can specify that says, yes, I want to do it anyway, and it will appropriately give you a warning that what you're doing is dangerous and maybe you shouldn't do it, and it will annotate the logs that you're running with experimental support, but it'll at least try the build, and you can do it if you really want to. So here's one, again, a developer-focused thing that I'm pretty excited about. So if you've opened PRs in the last I don't know, 2-3 months, something like that, we'll probably see that we've actually cut our CI over to fully being GitHub Actions based. So since almost the beginning of the project, we've used software called BuildBot to drive the builds for ZFS because it was easy for us to spin up VMs for different distributions and test on them. And because we needed some functionality that you couldn't get from a bunch of other CI systems, we had to be able to load kernel modules. We needed like full VMs to be able to do that. And that was hard to get in other environments. But Tino's recently done a huge bit of work to actually get us fully transitioned over to running our CI under GitHub Actions. And it works pretty well, in particular because it's doing something that you wouldn't think would work very well, but it actually works really well in practice, which is we spin up Ubuntu VMs under GitHub Actions, and then in those, we launch QEMU, and then run multiple sessions of that to do the build and the test. All right, so we're running QEMU under the GitHub Actions VMs for various distributions, and then spinning up a bunch of them so you can run the test suite in parallel, and then pulling together the results at the end to give you, quicker runs in the CI and parallelize running all the tests. So that's actually worked out really well. And one of the things I personally like about it a lot is it used to be that all of the CI machinery was stuck in BuildBot. It was hard for anybody else to maintain and work on. All of this stuff now is just config files in the .github directory in the repo. So anybody who wants to help improve the CI or work on it, it's all available there. You can modify it, you can extend it. We were talking about Z-test earlier and how we'd want to maybe improve it. It's all there, right? How it runs, how it can be configured. So I think this is a great recent addition. It's included in the 2.3 release, but it's more infrastructure. One of the other nice things about it too, right? You can see we've actually got FreeBSD. I'm not sure if you can see that or not, but FreeBSD is in the list there too, which is being run under QEMU on an Ubuntu builder. So lastly, what I've got is things that have been maybe on the roadmap for a long time, for things that we might be able to get in the next OpenZFS release, whether that be 2.4 or 3.0. Again, it's not an exhaustive list. We've got lots of interesting things people have been working on. But I know these are things that have been of interest to people for a long time. So the first one here I find kind of amusing because it's like the issue number is after it there in parentheses. This is issue 8 on the tracker, right? We're at like 16,000 now or something like that, right? So way back when, in the first 10, right, was to get a full Fuse implementation going that we could run in user space. I still think that would be really interesting, and I'd love to see that happen. We keep getting closer and closer to it as we improve the user space support in ZFS, but we haven't quite fully integrated a full independent implementation that all runs entirely in user space as Fuse. We laid the groundwork for a lot of that when we did the work for FreeBSD and Linux and splitting it up. You could imagine another supported platform there being just Fuse and a full user space build. Another thing people have wanted for a long time, force pool exports, right? There's a PR open for this. A ton of good work was done on it. It just quite hasn't been wrapped up yet. I'd love to see this in a new future release too. Again, with a lot of these things, it's just, it gets complicated. Like the last little bit, you can get it basically working, and then you're like so close, but there's a little bit more to do to make it actually reliable and solid. Like we were talking about before, about making sure all the tests in the CI run reliably and people get good feedback. I think, making sure the tests run reliably and it works as expected that last little bit can be a big lift, right? There's another PR open for Cha-Cha-20 poly encryption, right? This could be used for low-end systems. There's some good work out of LANL also going on for like the ability to like offload checksums, compressions to like a hardware accelerator, right? So that's additional work that's underway. I would love to see get wrapped up. Another one on my personal list of things I would like to finally see integrated is support for FiMap. I'm not sure if people are familiar with it on the Linux side, but it's just a better way to report like file layouts for things like copy, would take advantage of it, so they know which parts of a file are allocated and which ones aren't, so it can just copy the relevant bits. This is another one where we just need to probably rebase it and think through it hard and address any remaining loose ends. But it's been outstanding for a while. And like we've talked about in the past, I think it'd be great to pull in Mac OS support as another supported platform to the code base at some point. Jorgen's done a ton of work on that. It's in pretty good shape. We just have to, integrate all of that code into the repository. And now that we move to GitHub Actions, it actually gets easier to set up a builder to test it and verify it. So there's some infrastructure work there that maybe we're in a better shape to actually, make sure it works properly. So with that, that's all I had. But I'm happy to take questions about any of those features or any features that I overlooked that people are interested in, or just questions. Yeah.
One of the features you mentioned was the accelerator stuff.
Yeah.
I remember there was a talk about that at the OpenZFS Developer Summit a while ago. One question that I remember was asked at the time that I'm not sure if we have an update on is is the hardware accelerator available? Is that a commercial product, or was that some custom board they made?
So I don't know in particular. I know that there are accelerators available. I don't know if that particular one is generically available. But this is the kind of thing that you could imagine, with their accelerator, or maybe even conceivably being able to offload it to a GPU or something like that, right?
So in theory, you can plug in an Intel QAT, which is generally available. The one we used was from Identicom. It might be generally available. So.
Plug and play.
Curious about the pool export, the forced pool export.
Yeah.
If you export a pool and it doesn't export because you got open file handles and you fail over, you got to have guards so you don't fail back, because if you do kind of reappear the devices or whatever, all that I/O is going to end up flushing through. Does this kind of clean that up so you kind of are clearing all the I/O out, so you kind of don't have to worry about stale I/O sort of hitting the pool after sort of the world has changed?
Yeah. That's basically the idea, is for a forced pool export, you're forcibly canceling anything in flight and throwing it on the floor.
Nice.
So so you shouldn't have to worry about that, right? It should get all canceled. And that's hard on Linux. It really doesn't want you to throw it away. It really, holds references and everything, and it's hard to tear those down. And that's been a big struggle, letting it do that, right? But the idea is, when you do a forced pool export, the understanding is that you're willing to throw away anything that's in flight at the moment and just tear down the pool, unmount it cleanly, because right now the only other option is to reboot the node, which is terrible if you have multiple pools on that node and only one is suspended.
Yes.
Right?
Yeah.
Yeah. This is one I know at Livermore we'd make a ton of use of too, because when bad things happen, we don't want to reboot the node if we don't have to.
Yeah. Fantastic. That's one of ours.
All right.
Yeah.
So we should talk more about finishing.
Kind of more of a future question, I guess. Maybe to add to the thought queue, I tend to be more of a disk person in my experience, and so I think something that would be really cool as I'm thinking through this and looking at all these just freaking amazing features that are coming up right now. There's one thing, there's an image I have in my mind, because it's something I deal with on a regular basis, is you have disks that have typical, disks have their life cycle. They all have different, they all have, depending on the type of disk, they have certain uptime, certain power on hours. We all know what it is, 45,000, 50,000 hours. We all know what it is. And they all have a certain number of PHY interfaces in the back that connect. And so you see a lot of these errors and stuff. And so, yes, I know there's a bunch of stuff for IO stats and everything else, but it would be really cool if there's a way to kind of integrate something sort of like Oracle's FMADM, where you have a view to just say, in this pool, I have these disks, and just use standard SCSI SG commands to pull out the uptime, to pull out, the number of, the number of PHY interfaces that are available, because if it's less than XYZ, then you can look at a table. If it's less than that, then that drive needs to be reseated. Maybe the number of SCSI errors or whatever that you might see, something like that could be integrated into the file system would level set the playing field and make something that a lot of vendors try to proprietarize, something that could be more open. So that's my thought.
Predictive analytics.
Exactly, yeah, what he said.
So I agree. That would be very good stuff to have. What we have today, and what's been there for a while actually, like the zpool status command, let you can add arbitrary scripts to be executed with it and show additional columns. So you can see things like power on hours, temperature from the drive, smart status, and whatnot. You can get additional columns for that, but the zpool status command. But
What I was thinking about, my thought was add on, was to take everything that you just said, it's already there, but add it to the dash E command.
oh, sure.
No, just put a dash AI command out.
Just show me what I want to see.
Yeah, I mean, because you only want to know the ones that are having an error status. These are some of the possibilities that could be causing problems. So just, that's less development than just adding a flag. So just throw it out.
Yeah. No, that's a good idea, where you could include additional information where you know there's something not quite right with this drive, just to surface it so you can see it.
Yeah, this particular tool is either having some latency or some degraded status or it's not the IOs on its side, and here's some additional stats in the verbose mode to say these are some possibilities.
Yeah. The tricky bit there usually is deciding what's bad and what's not, right? You're like, oh, you remapped 2 sectors. Okay, that's not great, but it's not the end of the world, right? So, yeah, good ideas.
There's a remote question that's hopefully in context. What happens when the compression isn't one-to-one, identical to the deflate in OpenZFS?
If you're...
I'm guessing this is related to the offloader, yeah.
Go ahead, Alan. What was it?
I'm not sure.
So we already get that.
Cool. So we already have that. The accelerator we tested with does not write exactly the same data out as software compression, but it's fine. All the checksums are correct. It reads back just fine.
One caveat with somebody that wants to accelerate ZFS, it's like it does need to be compatible in the sense of the accelerator goes away, we still need to get the data back from ZFS. So that really would be on them to make sure that happens.
I know one of the things we're looking at for the accelerator too, is right, to always have a fallback software option for that kind of thing. So like even if you didn't have the accelerator, right, it was written in a format that you could get it back with a less performant software solution. Preferably the existing one.
Right, it's not a different compression algorithm. It's not offloaded gzip, say. It's actually labeled as just normal gzip.
Is there a way to test like these accelerators in the CI? It's like there isn't.
So normally you wouldn't do this, but we have a fallback testing accelerator that just links directly back into ZFS for functionality, but obviously you wouldn't normally do this.
Can you talk a little bit more about the phi map and sort of what that brings?
Yeah, so phi map has been my personal wish list for a long time now, right? So this is the interface that Linux provides. I don't know if FreeBSD has something similar. But basically, it's an interface you can request of a file, and it'll show you like what the extents are on a file, where they're mapped on disk, right? If they're compressed or not. There was talk about adding like encryption flags for it, so you could actually see like, okay, here's a file. How is it actually laid out on disk? And it's useful for tools like copy mainly, right? So it'll only copy the relevant bits of the file, right, where there's actually data. And it's just generally useful for inspection of files. Right? There's tools on Linux to dump like what the mapping looks like. You can see how it's allocated. Particularly useful for network file systems, right, where you don't want to be sending a bunch of zeros back and forth. There's been some improvements on the server side with sendfile and stuff like that to improve performance there, but like just having a generic phi map implementation would help NFS in particular. Right? It would take a little bit of work still to wire that up to things like NFS or like Lustre, if you're running Lustre on top of ZFS.
Yeah.
You need to wire, first you need to have the implementation in ZFS to get that data, right, that's reliable, and then those other file systems need to layer on top of it to expose it.
It sounds like it could be helpful with ransomware detection as well, because you'd see like a lot of change and be able to see it in sort of like a like just a extent list instead of having to like reread the data. You can kind of like see
Yeah.
how has it been changed.
Yeah. All right, well, if that's it.
My talk is finished. Thanks for listening, and I'm ready for questions online. There are one task from the waitlist and add the task into the run queue. Then they can execute their wait for their one. From where we suspended last time. So when the L request of the L2 is done, it works the same as for the L2. Since we have separate stacks, after doing all of this, we can run
All right. Have a seat. We're getting started. All right, so next up, we have Dengyu Sun joining us live from Beijing, China, where it's very early in the morning for him. So thank you very much for joining us. He's pre-recorded his talk, so I'll be playing it here, and then we'll have a live Q&A with him on Zoom. So welcome, and I will begin the presentation.
Hello everyone, I'm Dengyu Sun from IOMesh. My talk today is Run UserFS in Rust Async Runtime. Let me introduce myself first. I've been working on distributed storage system and started developing libUserFS last year. This is today's outline. I will first introduce libUserFS and Rust Async Basics, and then talk about how we run libUserFS in Rust Async Runtime. In 2022, we brought ZFS into user space based on libzpool and Fuse. On the left-hand side is ZFS architecture, which includes ZPL, ZVO, and DMU. On the right-hand side is UserFS architecture, which utilizes the framework of ZDB and libzpool to run ZFS in user space. Recently, we took a step further and brought libUserFS based on UserFS. The motivation is in two ways. First, we want to turn ZFS into a storage engine for user space file system, because ZFS has many nice features such as copy on write and snapshots. When developing a new user space file system, we aim to build upon the existing features of ZFS. Secondly, Rust has become more and more popular because of its strict compilation check for memory and concurrency. Rust also has many useful features such as async await and its compatibility with C. So we wanted to combine Rust and ZFS. This is the architecture of libUserFS. On the top, we implemented libUserFS, which works similarly to ZPL. libUserFS provides some basic file system semantics based on interfaces of DMU. On the bottom, we developed VDEV file to replace VDEV file. It uses libARO to maximize disk throughput. Interfaces of libUserFS are divided into three parts. The first is about dataset and how to manage it. It includes init, dataset init, and dataset close. The second is Anode operations, which stores metadata like attributes, the entries. We can use get attr, set attr, or create delete to operate on the Anode. The third is object, which stores file data. And the object can be accessed by read object and write object. Then let me introduce a use case by a read example. If we are developing a network file system, after receiving a read request, the network thread will spawn a read task to the worker thread. If this read gets cache miss, the worker thread will submit a ZIO to the AIO thread and wait for its completion. When the ZIO is done, the AIO thread wakes up the worker thread so it can continue running. In this example, the worker thread is blocked until the await returns. In this thread model, all tasks can only be executed one by one. So we need some way to tell the worker thread to switch to another task when our functions need to pause. Also, libUzFS has too many background threads. In a 16 vCPU VM, libUzFS would create over 200 threads per pool for task queues. In kernel ZFS, those threads are cheap, but when we are running ZFS in user space, the cost cannot be ignored. Before talking about solutions, let me introduce Rust Async first, and then use knowledge of Rust Async to solve these problems. The simplest idea for concurrent programming is thread per task. Our example is to read some data from the device and then process it. If we want to increase throughput of this model, we need to add more threads. If we have much more threads than CPUs, then CPUs will spend too much time on thread switch. To address the problem, we can use asynchronous I/O. This model can give us high performance, but the cost is scattered code logic. In this example, one task needs to be splitted into two functions, one for IO submit, the other for data process. If we want to do more IO requests in one task, we need to split the task into many pieces. Then we even need to register callbacks in the callback function. This makes our code hard to understand. Now that thread per task model gives us sequential logic, the only problem is the high context switch cost of thread. So we can replace threads with stackful coroutines. The coroutine switch also needs to switch stacks and jump to another execution flow using jump instruction. But the difference is that coroutine switch does not need to trap into the kernel. This difference eliminates the most significant part of thread switch cost. Furthermore, because stackful coroutines uses stackful coroutines uses stacks to save context. What if we save the context using state machine? In Rust, if we use .await behind the blocking functions, the outer function can be compiled into state machine on the right. In my function, we will first call the pull function of the read, which registers read request and checks whether the read is completed. If the read is not completed, my function will return pending to the worker thread. This return statement works like context switch in stackful coroutine because it returns control to the worker thread. After the read is completed, this task will be waken up. Well, when we want to resume the task, we first check its state, and the state is read. Since the state is read, we should continue work we left. And then the read is processed, and we can set the state to the right. Then we can execute the write future like the read. In last slide, we saw read future and write future. They are structures that implement the future trait. They have pull functions to make progress on execution. When the pull function returns ready, this means that the task is done. And when it returns pending because of some event, the worker thread can continue executing other tasks. After this event is ready, the task can be executed again, just from where it pauses. Return to our problems. For the first problem that tasks can only be executed one by one. To solve this, we can implement libUseFS functions as a feature. When a function needs to pause, the pull method will return pending. After fixing the first problem, we can replace our background threads with coroutines. This reduces thread switch overhead dramatically. Next, I will talk about some possible solutions and the advantages of our chosen solution, coroutine feature. The first solution is to rewrite UseFS functions. We will rewrite functions as features manually, like what the Rust compiler does to async functions, such that we can call it as async function in Rust. This solution gives us high performance and low memory cost because it doesn't need no extra stacks. But it also needs a huge amount of rewrite work because all functions that may block need to be rewritten. For example, if we have functions A, B, and C, the function A is blocking, the function B will call function A, and the function C calls function B. In this situation, we need to rewrite all three functions because all of them, when we call any of them, they might block the thread. The second idea is to spawn a stackful coroutine to run C code. Then the Rust task can call notify.await to switch to another task. When the coroutine is finished, the Rust task can continue. In example shown by the figure, in the first execution of task 1 in Rust thread, it will spawn a stackful coroutine to the coroutine thread. Then the Rust thread can continue executing other tasks. When coroutine 1 is finished, it notifies the Rust thread to continue task 1. The advantages of this solution is that we don't need too much modifications. We only need to rewrite those logs or CVs and other system calls that may block the thread. We don't need to rewrite all functions that calls them. But the disadvantage is that every call needs at least 2 thread switches to finish, even for non-blocking calls. In our example, the task 1 will first be executed on the Rust thread, and then part of it must be run on the coroutine thread. After the coroutine is finished, we need to execute the remaining code on the Rust thread. So can we combine stackful coroutine with Rust future? If we do that, we got coroutine future. In this solution, C functions continue to run inside stack for coroutines to minimize code modifications. And the coroutine is designed to implement the future trait. So we can pull the coroutine future on the Rust thread. If the target function is non-blocking, our first pull of the coroutine future will return ready. Then we can do others. Then the task is done. We don't have to change to any thread. This is the simplified pull function of our coroutine future. It works as follows. In the pull function, it will first call jump f context, which saves the current context and jumps to the target function. When the target function pauses or finishes, execution flow will jump back with the coroutine state set. And then the pull method can return based on the coroutine state. If the coroutine is pending, then the method returns pending. If the coroutine is done, this method can return ready. This slide shows an example of using coroutine future. The usage is in 3 parts. The first is the interface for external caller. The second is arguments for external C function. To run the function, we need to create a coroutine future and pass arguments and Rust function to it. The Rust external C function will call a C function libUserFS object read. This function is implemented in C and exported to Rust through bind chain. After doing all of this, we can run C code in coroutines context. Also, to detect pending state caused by conditional variables or mutexes, we need to re-implement synchronization semantics. We implement a coroutine futex, which has similar semantics with the kernel futex. It also has wait until, week 1, and week all. Then let me show you an example of task execution by using ZL wait example. The pending point of ZL wait is CV timed wait of ROCV. Since we have re-implemented conditional variable, so when we want to wait on the ROCV, we will first mark the current coroutine as pending and jump back to the pull function of the coroutine future. Then the worker thread can execute other tasks. Our first task is ZL wait for ZL1. In this task, we will first call wdev our start to submit a ZL to the AL thread. Then it will call CV timed wait. In this function, it will add this task in the wait list of the ROCV. And then the execution flow will jump back to Rust pull function. Then so the executor can execute other tasks. Before ZL wait for ZL1 is done, the thread can continue executing the CPU task. After the CPU task, we can execute ZL wait for ZL2, sorry. ZL2 task works the same as ZL1 task. It will add itself into the wait list of ROCV2. In this state, ZL1 task and ZL2 task are both waiting on its RCV. When the IO request of ZL is done, the AIO thread will call ZL done. In ZL done, it will first remove ZL1 task from the waitlist and add the task into the run queue. Then, the execute can execute ZL wait for ZL1 from where we suspended last time. So when the IO request of ZL2 is done, it works the same as for ZL2. Since we have separate stacks, the Rust stack and the C stack, so GDB, if we do nothing, GDB cannot backtrace from the C function to the Rust function. To resolve this, we need to set the C frame, the frame pointer of the C in the C frame to connect to the Rust frame. In this example, frame 0 to 3 are in C stack, the coroutine stack. Frame 4, 5, 6 are in Rust stack. We have also conducted benchmarks of coroutine implementation and the pthread implementation. Because IO depth of pthread version is limited by thread count, it achieves lower throughput than the coroutine version. And in other benchmarks like async write and metadata operations, the performance of both implementations is nearly identical. My talk is finished. Thanks for listening, and I'm ready for questions online.
Okay. Questions for Dongyu about ZFS and Rust async stuff? Yeah, go ahead, Alan.
So when connecting the existing C code to the Rust code, did you find any bugs in the C code?
Yes, I have found one. When we do a read after a write in some situations, but the details is hard to explain here. The situation is that when I write some data and then I do a read, and the read may return all zero data. Yes, I have found this the problem yet.
Other questions? So, go ahead, Paul.
So I was wondering how is the Rust code that you did, is it like living in a separate repository from the ZFS code, or did you integrate it into the ZFS code base?
Yes, the Rust code is in a separate repository. And in the slide, I have shown the link in GitHub.
Yeah, I think there's there's the link to the, I guess, the modifications that you needed to do to connect it together. Yeah.
Does that that GitHub also include like the work you did for the, you mentioned there's a like VDev AIO, VDev type now. Is that also included in that GitHub, or is that separate?
We now have two repos. One is the Rust code, and the other is the ZFS code we have modified. The ZFS code is in another repository, and you mentioned the VDev AIO file that is in the ZFS repo.
So while you were talking, I was also kind of like spelunking your code online. Great job. One thing that I didn't have time to look into, but I'm curious, if you build your code that way, did you kind of like add all these new infrastructure as like a different kind of like target, like how we have different OSs like Linux, FreeBSD? You added these kind of like user land differences as an extra thing, or did you just, you know, build on top of libzpool and just like don't care if the other things compile?
Sorry, I didn't get it. I didn't get your question.
The question is about like the basic, like how did you treat this target? Like there's Linux, there's FreeBSD, there's the userland, and, like libzpool, and then there's what you did, right? And how does like what you did like integrate with those other things, or does it not? Is that paraphrasing?
Yes.
Yeah.
Our build is on the DMU layer, so we haven't based on the DMU, we build a libUserFS. This is not about this is different from Linux, but now we only support Linux for now. But I think it's different from the ZPL in kernel ZFS.
I think that answers the question.
Yeah, I think maybe your question is also getting at like, for like you must have changed, like you changed like mutex enter and CV, you know, CV timed wait and sleep, like all these kernel functions that have already been abstracted out in the ZFS code base. So they do different things on Linux, on FreeBSD, on POSIX, userland, and now they have to do something different for Rust, like when you're running on the Rust async runtime. And I think you're asking like how it sits alongside those other three implementations.
Yeah,
right?
exactly.
Like, did you just change the POSIX implementation to be like, oh, there's no POSIX wait, like there's no POSIX sleep anymore, there's only Rust sleep? Or is it like some new file that has the Rust implementation?
Yeah, yes. For example, we have rewrite the implementation of the mutex. After our version of mutex, when we use pthread, the pthread lock may block the thread, and the coroutine mutex will only block the coroutine and switch tell the scheduler to switch to another. Is this your wanted?
No, I think my question was indirectly answered.
Okay.
Yeah. So, yeah. Thank you.
Other questions? Cool. I think that this work is really interesting. I know it's not necessarily applicable to everyone here. Obviously, we're not all trying to integrate ZFS with like a Rust runtime. But I thought that it was really interesting how, Dongyu, you've taken advantage of the fact that like ZFS works on all these different platforms, and we've already abstracted out like everything that you could possibly need, like mutexes and CVs and waits and sleeps and all these things, so that it can work on Linux and FreeBSD and in userland. And now you've kind of added a new backend for it, which I think is really neat. I was thinking about how this might be applicable to other like Rust projects in general, like interoperation between Rust and C. And I think it might be, but what's kind of unique is that with ZFS, we already have this giant C code base that's already abstracted out all these like super low level interfaces that you needed to replace for, to make it work in this different runtime. So I think it's a really neat application of the code base that we've created and how we've abstracted it out, and then integrating it with this like newfangled, like very, compared to like threads, it's a very newfangled runtime environment that you never would have really thought that ZFS could work in. So I think it's really neat and look forward to seeing what you guys do with it in the future. Thanks a lot.
Thank you.
All right, I think that the, Michael, did you want to give a little bit about the user conference wrap up? Okay. Okay. I was just going to go through since I think it probably we have time. If you have, all right. All right, so we'll be here in just a moment.
and you all have been awesome. So not everyone caught the first few days of discussions, but day one especially was very intense on here we are, here's what we do, here's some ideas, and we just pounded through. We had Mav and Alan at our disposal and had some excellent developer feedback. And I'd argue it was magical. So we will have those recorded. There's a lot of wisdom hiding in them. So it's on all of us to go through those recordings and hear some of the use cases, hear some of the real world activities. I had a great time. Show of hands, enjoyed it? Great. So I have produced a little list of things that were both low-hanging fruit and not so low-hanging fruit. And if someone has a strong point from all those notes I scribbled, please come on up and share that. But I will go through what I heard and what was the most tangible of things that production users have identified in the wild and would like to just get on the radar of a developer or two in whatever way we can. So borrowing from Matt's document, I took the non-technical one, conference organizing. Doing okay? Cool, okay, moving on. Finer grained delegated commands, especially destroy. Oh, user Pat can delete a snapshot. Great, they're our snapshot operator, that's their job, they're excellent. They can also delete a data set. Not so good. I don't know what the perfect syntax would look like, but some finer grained controls there would be great insofar as an unprivileged user can't wipe out the majority of your storage. And multi-tenancy. And on that very point regarding multi-tenancy, and you can phrase these however you please, this is what I heard and how I interpret it, but there's probably a more accurate term for each of them. User-based list privacy and filtering and other commands such as, I'm going to list data sets. I see the entire home directory in every user's data set. I see the accounting department and all of their breakdowns. Every data set is visible to every user. We had some great discussions about how container environments have various mechanisms to hide stuff so that you think you have root on a system and all you have is a container down in the deep down over there. So hopefully you see the concerns to folks like the hosters in the room who have a whole lot of users and really don't want to have people know that the competition is on the same box and just kind of privacy. Anyway, moving on. You all know this best, but well, what do 2025 sane defaults look like? The moment OpenZFS hit LZ4 compression and the asynchronous destruction, I thought we have the perfect file system. Everything else is icing on the cake. So there were a lot of discussions like, well, are we still assuming people are not using LZ4 in various circumstances? What checksum algorithms are best for defaults? And that's going to mean something different to every user. And there was a phrase, what does checksum equals auto look like? I can't answer that, but just broadly, so much water has traveled under that bridge. Let's just look ahead. And I don't know if that's a OpenZFS 3.0 question or not, but there it is. So compatibility aliases. These are awesome. I will never type ZFS list-t snapshot again. Once there was snap and I learned you can do it in 4 letters instead of a bunch, I'm like, great. So then I instantly thought, new system, I will allow myself to snapshot. And I'm like, allow Dexter snap data set name and pool data set. And it's error, error, error. And oh, the shorthand hasn't made it into the delegation allow code. So I'm like, oh, okay. And I think Rob, who came up a few times and was here on the wire yesterday, I believe on a production user call, I'm like, why can't we just type like list-tfs for file system instead of file system? You're like, oh, duh. So I think it might, if someone has a moment, please look at the shorthand and just think, okay, is it consistent across the board? Is it consistent for allow and not just list, etc.? And so, thank you. The comment was, we don't care as long as it's consistent. I'd argue short and consistent. So FS or something. Anyway, and the examples here are just snap, ball, FS, just instead of that. This came up a bunch and you each have a different answer, but Recursive consistency. I'm sure great progress has been made. I don't know if the rough edges are still out there, but a user should sit down and think, oh, this recursive operation will behave more or less like this other recursive operation I performed. I'll let you answer exactly what that means, but moving on. I've heard regrets, and I encounter this ever trying to explain ZFS to someone. There's the implicit data set that when you create a pool, you get a data set with that pool name, and confusion begins. Some people never see it, never care. Some people get very hung up on it if you, say, have an encryption root. And I don't know if you can set it, the implicit data set as encryption root, but you'll probably regret it. We don't have a time machine, but if one could minimize the role of the implicit data set and maybe even properties that can be set, I don't know what the proper solution is, but looking to the future, maybe the volume management and file system management should be separated further. I'll leave it at that. We had a great discussion on what libZFS guarantees look like for different people using different languages. I understand there have been handshake agreements regarding Python for various, be it products or you name it. We are not here to restrict developers and make their lives difficult and contain them in some spec set out long ago, but we do want to find that balance that allows person with their language of choice to move mountains with ZFS using API interactions with it. It's above my pay grade to say exactly what that looks like, but maybe revisit that conversation. It was intense, it was great, a lot of good points, and I trust everyone in the room has some definition of that. Hopefully there's this Venn diagram that puts a few in the core, like what core guarantees can we make and what can we fully disclose are being a bit wild and will change and just go in understanding that. Moving on. This is on absolutely everyone. Documentation. Documentation from 20 years ago still pops right up. Documentation from non-OpenZFS pops right up. There are a lot of best practices out there that made a lot of sense a very long time ago. Whenever you find an opportunity to hop in and, say, blog about a thing you found, do take a moment to see if it would also be appropriate for the manual pages, and then trickle on down through official documentation. Also came up with some notion of a pre-flight suite. I've long envisioned this, that we have a new piece of hardware, and I will kick off this script and go to bed and wake up to a report on what it does well and does not do well, step through all the RAID Z configurations, step through D-RAID versus RAID Z versus just all the things, record sizes with equivalent test suites to say, hey, I want it to behave like a video editing, media distribution, whatever server with very large block sizes. I want it to simulate a database. I want to do all the things. I'm sure every single person in this room has something in their toolkit that they've done. If we can go kind of stone soup in there and bring those together, I think good things will happen. Oh, small typo. We also had a great discussion, especially with Rob and Olivier. So people like containers, be it Docker, be it jails, be it zones, be it you name it, and things like stacking data sets and whiteout support and UnionFS and the OSI spec. When you look at certain specs, and I keep repeating this, it's like, tell me you have a terrible 1990s overriding file system without telling me you have a dated 1990s overriding file system. We have so many abilities that aren't available elsewhere. I think consensus was there are opportunities for just a few hooks. For example, transparently stacked snapshots or data sets where they don't completely override, but there's some notion of UnionFS mounting. So fortunately, Olivier and Rob and Jan continued chatting, like as we were all doing our thing. They will continue that discussion. If you have real-world use case experiences to introduce to that discussion, they will turn to the various Slack channels and mailing lists and all to make it happen. Because I'm sure we all define it a bit differently, but I'm sure there are opportunities for heavy lifting within ZFS to just make it easier. So some of those are low-hanging fruit. Now, Some of you have bumped into these things. Greg chimed in about his experience. Yes, there's a show. Hand him back. Okay. Better destroy freeing estimates for now. Okay, so that came up. Cool, thank you. So that was a right. The idea that if you delete this one, you'll free that. But then suddenly this one's bigger, and you're kind of playing this whack-a-mole with it, moving around. It's like, well, great point. Let's get on the list. And I'll go briefly into the I don't know if we have a universal term for it yet, but audit all the things. A lawyer-friendly, a discovery-friendly audit history of everything that took place by every user ever on a storage system, which I know is a ridiculously monumental task, but for some it means just kicking on Samba auditing, which absolutely has a performance penalty overhead, meaning the further you push it down the stack close to the kernel, the more efficient it is. So if a disgruntled employee disappears from a company and a bunch of stuff disappears, folks would like to know who did what exactly when and where and see that auditing log. There are related discussions about how the ZPL history ring buffer sometimes shows absolutely nothing of what you'd expect was there. Sometimes a -I flag helps. Sometimes a certain utility might not use whatever resources to give you that history. And I've seen this in the wild during a development effort where it's like, I created a bunch of data sets and there's no history of it. I probably didn't know about -I at the time, maybe it didn't exist, but suddenly what I did didn't happen, and that's really not an exotic use case. That's pretty basic. So you can also drown in history if you're very aggressively snapshotting and deleting and keeping track of something. It's like, no, we don't need a fire hose of pretty routine, meaningless information. But at the same time, if that disgruntled user is out the door and wiping out the accounting data set because they had permission, because they had snap deletion delegated abilities, these are very real world issues. And the Hollywood has the MPAA Trusted Partner Network. And a studio that shall not be renamed had a movie just disappear onto the internet through various hackers, and that upset a lot of people. And they really don't like, be it screenshots, be it previews, be it whatever, of a new upcoming movie slipping out. So they've really tightened up on who can do what. That makes for a lot of VDI sessions for remote editing where you never do touch an actual system, you just get a vision of a system. And throughout, a consistent message is just log all the things, as mundane as they are, and each user has a different set of priorities. Some care about those deletions, some care about, maybe creating is just as dangerous as deleting. It takes many forms, but the more that we can do within OpenZFS, the better, or facilitate up the stack. In the discussion, we got into, okay, well, gee, you've got your NFS users and your SMB users, and not our problem, but also ZFS is really good at storing stuff so that if that information should be there and simultaneously to multiple syslog servers, and whatever form that takes for your use case, great. But any and all tools that exist and are at the table within this room, please come forward with them and say, hey, we've done this and brought this far. Maybe we're missing a certain functionality. There were some very clear third-party proprietary software solutions that are available in a broader context, but not just as a single, here's your MPAA compatible overlay for N number of dollars. But we're just, Greg described how, despite loving ZFS, it was a deal breaker on a pure Linux or FreeBSD system for that purpose. They had to turn to a proprietary solution. So let's just help people out with what we have under the hood. That all said, are there other production users who would like to chime in? Go ahead and bring up number one.
just had a quick question because I know it's kind of tied in with number 14 and another one up there, I forgot where it is, where you were talking about encryption. Like, it seems like there's a little bit of let me back up. Like, in terms of like support for FIPS encryption 142, 140-2, and 140-3. Like, it seems like some vendors or some of the hardware vendors kind of had their own implementation of that, but I feel like it might be something that might be worth putting into the open source, distribution of it, because a lot of the more secure environments, not necessarily government, kind of request FIPS and LUX. So just wondering what the community thinks about that.
Remarkably, encryption didn't come up because we had so much to discuss, but that itself is a fascinating, deep topic.
That require FIPS and more so FIPS.
But they also require the auditing side of FIPS,
Exactly.
which is why we're focused on the auditing side.
Well, okay, true.
Encryption's
Yeah.
encryption. How you audit the encryption was the critical point.
Right, but at the same time, in order to be able to qualify their standards and their, to check off their check boxes, they have to say we're FIPS compliant.
Sure. Golden check
We were
box.
going for the hard task, not the easy.
Yeah, exactly. I'm just trying to check off the box.
Fair enough. Maybe in the hallway track we can bring that up because that absolutely, we could have dedicated a day to encryption, and then like we did the auditing.
I'm not a fan, but some people just need it.
We could do a day on testing too, and just standardized testing of what testing means.
The comment was we could do a day on testing. What does testing mean? Because
Yeah.
clearly the ZFS test suite, and as Don pointed out, yep, it'll do what you asked it to do. That might not be what you want, but it'll punch through and go. That's for a developer. But, moving on. Other recollections, I know there were questions about, say, faster import in HA environments. The underlying code is getting really good, but when you get complex, suddenly the issues get equally complex.
I mean, there's a whole
A microphone? Stu? Please. We want to hear you.
Integration layer on, hey, ZFS is, it's a Linux product. It's a good thing to do these small things, and it does a huge amount. But Oxed, grep, ZFS is one of those things. What we put on top of it and how we manage it and everything else from an operations standpoint and a production standpoint, all of these things are feature adds that make our life easier. Can we do it all? Yeah. But if we can push it into ZFS, or at least get the hooks into it to get the data out in a sane manner, we can make the stuff sing and dance with a real easy overlay. And that's really what's driving everything on our production list. Is if you make it simpler for us, we can deploy this wider and wider and wider to greater impact.
And OpenZFS is just about the most portable file system after FAT32, such that if you want to dual stack on, be it Linux, Lumos, and FreeBSD simultaneously, you don't want to reinvent auditing on all three. You don't want to reinvent the encryption on all three. You just...
I want to hook into HA, whatever that means to whatever customer. It's just, hey, this is an HA-enabled one, so I need to know that, hey, I can have two nodes talking to me at the same time. One's in read mode, one's in read-write mode. That's not going to panic everything. Those type of scenarios.
Do you really speak about concurrent pull import on two systems? And how do you expect handle pull being updated on disks?
Different conversation. Yeah.
Repeat the topic.
To be able to actually have basically and Alex, tell me if I'm wrong, have a read-write system and 17 read systems that are all hitting the same data pools or data sets to actually feed it. I mean, that's one of the high HA type of environments that have been asked to be deployed. So I don't see that as a clean solution right now, but there are crutches we use to make that happen. So whether or not that's a native ZFS, OpenZFS thing to enable it, I don't know. And a lot of it depends on the hardware architecture and the network architecture underneath of it. So it gets to beyond what the core focus of OpenZFS is, but if it's something that can be enabled and then bolted on functionality, that solves some of our customers' problems.
The question, how often do you want that read-only system to see updates? If from time to time, then you can create pool level snapshot and import
Right.
snapshot. That's
And which is,
support.
yeah, right. You do that once an hour and that's good enough, or it needs to be transactional and it needs to be every 13 seconds.
Then
Yeah.
at some point it may not have solution.
Right. So I mean, those are the things that as you're looking at what is in ZFS 3, you know, what other things are we trying to accomplish above OpenZFS that might have architectural impacts into design? Yeah. Not everyone needs an Olympic-sized swimming pool, but there are a hell of a lot of hot tubs are out there. They all need water pumps.
Anything else as we wrap up day 3? Yes, Paul.
I was just going to say that there have been a lot of good changes to the import code for parallel import, but one place that does still need a lot of work is that the SPA namespace lock is a very big hammer in the kernel. We use it to guard a lot of early import. It's used to guard a lot of VDEV configuration stuff. It's used all over the place, and that is, at least in some use cases, currently the bottleneck for parallel import. So if somebody wants even better parallel import performance, looking at breaking up the SPA namespace lock or like refining it down to the places where it's truly necessary might be an interesting project.
Yes, sir.
On that note, if anybody remembers anything else from the ideas for hackathon from Saturday and Sunday, the spreadsheet is up to 20 rows now, but that's from 2 a couple minutes ago. But,
Okay, yeah, we've got some.
If you have any other ideas that need to make it over to this list for tomorrow, very open to those ideas.
You're free to copy these right over and assign yourself homework, but you know, we're trying to be
I
reasonable
grabbed 1 or 2 of
users
them
here.
already. But I added your name beside some of those, Don. Yeah, you do.
Happy to discuss all this ad nauseum, so if there's anything that needs clarification.
Yes, please.
We are here. I'm not going anywhere.
And we should be quiet by 11, but the key to the building is in my pocket, so we can hack all night if needed. So there's 3 couches, enjoy, no shower, but let's hack. Anything else as we wrap up?
One last thing.
Yes, please, Matt.
Always one last thing.
Thank you so much, Michael.
You're welcome. My pleasure. My pleasure. My pleasure.
It is, personally, and I know that the conference would not have happened without all of your work this year. So thank you so much.
You are welcome, and I was about to thank the hell out of my crew. So thank you, Matt and Karen, to begin with, because they're like, let's meet. And I'm like, okay. And then let's say Patrick. Thank you, Patrick. I mean, the magic for getting our remote presenters in. Stu and Santi, the kitchen crew, Argentinian barbecue and pulled pork tonight. Nick, who couldn't make it today. The Freshes, you've probably seen them at other events. Lisa and Andrew, delightful people. Rod Grimes has been super helpful. Andrew Hedinger, ridiculously helpful. Thank you. Helped me with the Cookie Monster run today. Archie, oh yes, so breaking news. Yeah, Archie brought his a selection of audio, video, balanced microphone interface things that made all the Zoom stuff possible, like at the perfect moment. Just like, here you go. Thank you, Archie. And thank you, all of you. Without the developers, we can just sit here whining as users, and with our overriding file systems, yeah, no, the 90s were cool, but let's look ahead. Anyway, thank you all. Stu, how long on dinner? It is now, 4:30. We have time for social time. We have countless beverages, uppers, downers, Oh, whiskey collection. Oh yeah, we're about to start. Yeah, I won't go into detail, but thank you, everyone. I can't say that enough.
Everyone be nice to Michael so he does this again next year.
Don't. Show of hands. Bay Area or Portland, Oregon? So first, downtown San Francisco. Let's see those hands. Let's see those hands. I see 1, 2, 2, 3, 4. Oh, you Bay Area kiddos. 5. Portland, Oregon. Okay. Thank you. Oh, well, yeah. Awesome. Thank you. Take care.
Wherever Michael wants to organize it.
Oh, geez.